There's something about this shape that still feels futuristic. No fuselage, no tail, just wing. But what you're looking at isn't new. It's a design that's been trying to prove itself for nearly a century. This is the Northrop N9M, a small experimental aircraft built to answer a very big question. What if the most efficient airplane was nothing more than a wing? That question didn't stay small for long. By the end of World War II, it had grown into something massive. The YB-35, a bomber unlike anything the world had ever seen. No tail, no compromises, just pure flying wing. And decades later, the idea would finally come of age. The B-2 Spirit, a design once considered radical, now defined the future of air power. Long before stealth bombers were even a dream, a podiatrist named Dr. Cloyd Snyder was chasing an unusual idea, inspired not by bird, but by the shape of a shoe insert. In 1932, launched by car and guided more by curiosity than certainty, it was one of the earliest attempts to answer a question engineers were just beginning to ask. Could an airplane be nothing more than a wing?
Here's the airplane of the future, according to its inventor, Dr. Snyder. He calls it the flying wing, and experts think it's going to revolutionize aviation. It's supposed to be foolproof and has lots of speed and pep, as the doc's going to show you right now. Here she goes. Looks as if the inventor copied his idea from a butterfly.
Not a butterfly, but a powered evolution of Snyder's glider, the S2. Just as the first flying wings were taking to the sky, a young aircraft designer named Jack Northrop was taking off on his own, forming a new company, the Northrop Corporation, in El Segundo, California. Born in Newark, New Jersey, and raised in Santa Barbara, California, Northrop came of age just as aviation itself was being born. He was drafted into the Army during the First World War, and like many in his generation, left it with his eyes on the sky. By 1923, he joined the Douglas Aircraft Company, entering an industry that was still wide open and full of possibility. From the very beginning, he showed a natural instinct for design, combining practical experience with a growing sense that aircraft could be something more. Working alongside the pioneers of the era, he began to develop ideas of his own. Ideas that would push beyond convention and help shape the future of flight.
Well, I'd had a little experience as a garage mechanic, and I had worked for a year as a draftsman for an architect, and I'd worked for my father, who was in the building business, and this sort of qualified me to design airplanes, you can understand that.
In spite of that unlikely background, Northrop adapted quickly to the world of aviation. In 1927, he began working with the newly formed Lockheed Aircraft Company at a time when aviation was still finding its footing. It was here that Northrop began shaping ideas that would set him apart. The Lockheed Vega, sleek, strong, and ahead of its time. Its molded plywood construction created a smooth, aerodynamic fuselage, reducing drag and increasing speed. It could fly higher, farther, and more reliably than most aircraft of its day, setting records and redefining what was possible in long-distance flight. It would carry pilots like Amelia Earhart into the history books and immortality, and Wiley Post around the world in his beloved Winnie Mae. By the late 1920s, Northrop's thinking began to shift. He wasn't just interested in improving airplanes. He was beginning to question their very shape. What if all the parts we take for granted, the fuselage, the tail, could simply disappear? In 1929, he put that idea to the test. The X-216H, an experimental design that blended wing and body into a single continuous form. Thick through the center, with a pilot seated in an open cockpit. It wasn't a pure flying wing just yet. Twin rudders, mounted on booms, still extended out the back. It was unconventional and unproven. For its debut flight, Northrop turned to pilot Edward Bellandy.
Well, Mr. Bellandy, this plane is quite a little different than those you've been used to flying. Wings are all metal and plenty heavy enough and strong enough so that a person can walk all over them almost anywhere.
Very interesting.
All right, Eddie. Well, if you're all set, let's go.
Goodbye, Eddie.
Bye.
In the air, the X-216H proved the idea had potential. It was stable, controllable, and unlike anything else flying at the time. But it was still an experiment, and the path forward was far from certain. For Northrop, innovation alone wasn't enough. While the flying wing continued to evolve, he knew he also had to succeed in the real world of aviation. This meant building aircraft that were commercially successful. So alongside his radical designs, he developed fast, efficient, conventional aircraft. Among them, the Northrop Gamma, a sleek, high-performance machine built for speed and distance. In 1936, Howard Hughes flew a Gamma from Los Angeles to New York, breaking the Transcontinental record, proving the Northrop designs could deliver on the world stage.
New York, millionaire, movie producer, and record-breaking aviator Howard Hughes. In his Northrop plane with the Wright Cyclone engine, he spanned the continent in 9.5 hours, breaking all records.
By the mid-30s, Northrop had his own company and a growing reputation. But even as business grew, he never lost sight of the flying wing.
Northrop decided to move ahead with his biggest dream, and that was to build a pure flying wing airplane. And the result of that was in the late 1930s, an airplane called the N1M. And that was the very first pure all-wing airplane built by anyone here in the United States that was to fly with any degree of success.
Northrop approached it methodically, starting with drawings and refining the shape into a true flying wing. Compact, experimental, built to see if the idea could really work. The experimental N1M had a broad, swept wing and no conventional fuselage. The pilot, engines, and controls all blended into the wing itself.
This plane, as you see it, is really a flying laboratory. And in the present arrangement, represents one of 15 or 20 different configurations that we've tested in about 200 flights made to date. We believe that we've solved most of the problems connected with the development of the flying wing, and that this type of plane will have considerable promise for future use.
I'm back up. Back up.
How does it fly, Moy?
Well, Jack, it flies as well or better than most conventional planes that I've flown, and its handling characteristics are perfectly normal. The feel is exactly that of a good conventional airplane.
That's fine.
He had been farsighted enough in the design of the N1M to create it so that it had a lot of flexibility. And when I say that, as an example, the wings were pivotable. They actually had at the root sections, they were designed so that he could change the sweep angle at his beck and call. He literally could disassemble part of the airplane. He could change the leading edge sweep angle, let's say 2 or 3 degrees, bolt everything back down, and then take the airplane and flight test it and see if that made any difference in the quality of flight. He had that same option on the wingtips. But through the course of his flight test work with this aircraft, he discovered, when all was said and done, that the airplane was most stable with basically a straight line from wingtip to wingtip.
The N1M's power came from 2 4-cylinder Lycoming engines, just 65 horsepower each, buried inside the wing to reduce drag. By the summer of 1940, the aircraft was ready to go. At Baker Dry Lake in California, Northrop's flying wing sat poised for its first true test. A handful of film crews were there, ready to roll, capturing the moment few quite knew what to make of. At the controls was test pilot Vance Breeze.
A plane of unusual interest is demonstrated at Rosamond Dry Lake in the Mojave Desert. It is the latest model of the Northrop Flying Wing. Developed from designs originated by Mr. Northrop in 1923, this bat-like plane is devised to use all its surface for useful lift. The elimination of non-lift elements such as tail and fuselage is what does the trick. The Northrop Corporation estimates that general application of this principle would result in speed increase up to 100 miles an hour with no extra power. And it is thought that this design will make construction 30 to 40% cheaper. It may revolutionize airplane engineering.
As the test program continued, Northrop test pilot Moy Stevens took over the controls. The N1M entered its next phase. Early tests showed it was stable and controllable, but overweight and underpowered. Also, flight could only be sustained by holding a precise angle of attack. As flight tests continued, Northrop made improvements to stability and control. Elevons, combining the roles of elevators and ailerons, allowed the aircraft to climb, descend, and bank without a tail. And at the wingtips, split surfaces acted as rudders, helping to stabilize and steer the aircraft in flight. Even the downward angled tips themselves were part of the experiment, later straightened as the design continued to evolve. With the N1M, Jack Northrop had proven his concept. But with war clouds gathering across Europe, the U.S. military was about to demand much more. In 1939, Germany invades Poland, a lightning war, fast, coordinated, and devastating. Then came the Low Countries, Belgium, the Netherlands, and soon after, France. And Britain stood next, alone and in the crosshairs. An ocean away, the United States watched, but it wouldn't remain distant for long.
It became apparent to the Army Air Corps and its parent, the Air Force, that sooner or later we were going to have a very large bombardment aircraft that was capable of covering enormous expanses of water and land. And the end product of all of that was a competition for an intercontinental range heavy bomber.
In 1941, before the United States entered World War II, Northrop was commissioned to develop a long-range bomber. Building on the success of the N1M, Northrop argued that a true flying wing could reduce drag and eliminate unnecessary weight. The result, he argued, would be faster, more efficient, and capable of flying farther than anything before it. But what the military wanted would have to be much larger than the N1M. a long-range bomber capable of carrying 10,000 pounds of bombs on a 10,000-mile round-trip mission. An aircraft designed with a single purpose: to strike Nazi-occupied Europe, even if Britain were to fall. On December 7th, 1941, Japanese forces struck Pearl Harbor, devastating the U.S. Pacific Fleet. In a matter of hours, the United States was at war. Almost overnight, American industry shifted into overdrive. Factories expanded. Production lines accelerated. Aircraft rolled out in numbers never seen before as the nation raced to build the air power it would need to fight a global war. Amid that surge, Northrop's new long-range bomber program, designated the XB-35, was moving forward. But before a massive flying wing could take flight, it would have to be proven. The answer was the N-9M, a one-third scale aircraft built to test the aerodynamics, handling, and performance of the flying wing concept. With a 60-foot wingspan, it would serve as a critical stepping stone, gathering data, refining the design, and preparing pilots for an aircraft unlike anything they had ever flown.
The four N9Ms were extraordinary because they incorporated all of the design advances and improvements and discoveries that had been made with the two predecessor aircraft, the N1M and the Aviation. They were very clean, aesthetically very pleasing aircraft. There were four N9s built, and there were many little subtle differences between those four aircraft. All of these configuration differences allowed him to test a variety of different options with the basic flying wing configuration.
The aircraft were originally powered by two 290 horsepower Monesco C6S-1 Buccaneer inverted air-cooled straight-six engines driving twin-bladed propellers.
N9M work concentrated heavily on establishing the criteria for the flight control systems on these aircraft. What you had primarily was a combination control surface, which was called an elevon, and that was the combination that would normally be input by an elevator and also the control forces that would be put in by an aileron. So Jack Northrop, along with his engineering staff, had to come up with a flight control system that to the pilot, when he got in the cockpit, everything looked normal.
In the air, the N9M began to reveal both the promise and the problems of the flying wing. Engine reliability was a constant challenge, limiting flight times and complicating testing. Just 6 months into testing, tragedy. During a flight, the test pilot experienced a control reversal while attempting to recover the aircraft from a right-hand 60-degree nose-down spin. The plane crashed, killing one of Northrop's most experienced pilots. But the program moved forward. A replacement aircraft, the N9MB, was built, featuring more powerful and more reliable engines. Across multiple aircraft, the N9M program explored new ways to control a tailless design. Drag rudders placed along the wing helped manage yaw, refined control systems, improved stability, and gave pilots greater confidence in the air. Each variation brought the design closer to something that could be scaled up into a true long-range bomber. By the end of the war, the N9M had done its job. Before it was retired, guest pilots had the chance to fly the prototypes. One of them, Captain Glen Edwards, is quoted as saying, "The airplane flew surprisingly well, was more stable, and handled far better than most would expect." Records are vague about the end of the program, but it's believed the last flight of an N9M took place in late 1946 or early 1947. Of the 3 remaining N9M aircraft, 2 were eventually lost to time, but there was one survivor. The N9MB, built in 1943, the one-third scale aircraft that had helped prove the flying wing concept, had sat silent for decades, a relic of an idea once ahead of its time. Back in 1982, in Southern California, a group of volunteers set out to bring it back to life. At the Plains of Fame Air Museum in Chino, alongside former Northrop engineers and enthusiasts, a restoration began. It would take years, but the aircraft was rebuilt and restored. Its structure strengthened, its purpose renewed. What had once been an experimental testbed was ready to take flight once again. The restored aircraft was powered by two 300 horsepower Franklin Flat 8 air-cooled engines, using a unique fluid converter to dampen vibrations. On November 8, 1994, the N9MB returned to the sky, more than 50 years after its first flight. Pilots and spectators alike could finally see what Jack Northrop had imagined. While the N9M proved the flying wing concept, Northrop was already looking ahead. In 1942, as the war intensified, work began in earnest on a full-scale flying wing bomber, the XB-35. It was a massive aircraft designed to carry heavy bomb loads across intercontinental distances, a flying wing built for war. The same principles Northrop had pursued for years: reduced drag, structural efficiency, everything contributing to lift, were now being applied at an entirely new scale. Building a tailless aircraft this large meant solving entirely new problems. Inside the wing, the aircraft would carry its crew, a central cabin embedded within the structure itself. With space for gunners, equipment, even bunks for long missions. Its payload was distributed across multiple bomb bays built into the wing. And in its final form, the aircraft would carry heavy defensive armament, turning the flying wing into a fully realized combat bomber. Alcoa introduced a new advanced aluminum alloy, stronger than anything used before, allowing the structure to support the immense size. Powering the YB-35 would be four Pratt & Whitney R4360 radial engines driving dual contra-rotating propellers. It was an extraordinary undertaking, an aircraft unlike anything ever built, taking shape in the middle of a world war. The war would end before the YB-35 could leave the ground, but that didn't deter the U.S. military. With a new Cold War already ramping up, long-range strategic bombers remained a priority, and by the summer of 1946, the YB-35 was ready to take to the sky. At the controls, Northrop's chief test pilot, Max Stanley.
My immediate boss as a test pilot was the chief aerodynamicist, Dr. William Sears, who contributed significantly to the development and the design of the flying wing. And he called me into his office one day and he said, well, you know, we're getting close to the first flight and we think that you ought to be the pilot, or words to that effect. Well, that really stunned me, but it actually I was overjoyed to hear it, and I went out of his office on cloud nine. But that's when I first knew that I was going to be the pilot. And that was perhaps 3 months in advance of the first flight.
In June of 1946, the XB-35 finally took to the air. A 45-minute flight from Hawthorne, California to Muroc Dry Lake in the desert. While airborne, the unique control system was put to work. At the wingtips, split surfaces worked together, moving up and down as a single unit for roll. But when yaw was needed, those same surfaces would open up top and bottom, creating drag on one side, turning the aircraft. and when deployed together, they could slow down the aircraft or adjust its descent. The control system proved effective. The engines, with their counter-rotating propellers on the other hand, began to show signs of trouble.
As good as the XB-35 had proven to be during the course of its initial flight test program, it did indeed suffer from some very serious problems. One of the biggest was the propulsion system, not necessarily with the engines, but with the very large, effectively 8-bladed contra-rotating propeller assemblies on the trailing edges of the wings. Contra-rotation gearboxes simply had not been perfected by the end of World War II. There were a number of airplanes flying with contra-rotating propellers, but they did so at some risk. Contra-rotation systems are very complicated. It's very difficult to keep them cool. Gear designs are critical. Metallurgy becomes an important issue. Strength factors are extremely critical, and the B-35 effectively fell victim to that.
The first problem was that the engines and propellers had never been fully tested together before being handed off to Northrop. Within just a few flights, vibrations were increasing, and the complex contra-rotating propellers, so critical to design, started failing with alarming frequency. There were high-level meetings between Northrop, the Army Air Force, the engine and propeller manufacturers. But responsibility was unclear, and solutions were slow in coming. Finally, issues with the aircraft's driveline got so bad that Jack Northrop himself grounded the XB-35s until the government fixed the propulsion system. Faced with mounting challenges, Northrop began to look around for alternatives. At the same time Northrop was developing the flying wing, another long-range bomber was taking center stage, the Convair B-36. Built to the same demanding requirements, carrying heavy bomb loads over intercontinental distances, B-36 designers took a more conventional approach. Massive fuselage, long straight wings, and proven systems. Powered by 6 Pratt & Whitney radial engines, it avoided the complex contra-rotating propellers that plagued the XB-35, and in doing so, sidestepped many of the problems Northrop was still struggling with. Despite ongoing efforts, the engine problems persisted. Vibrations, failures, and no clear fix. But just as the program was beginning to stall, a new technology was emerging. One that was about to change everything.
Fortunately, what was coming down the pike at about this same time were two things. Number one, the option of converting from a piston engine to a turbine engine, pure jet in other words, or going to a turboprop configuration wherein you utilize a jet engine to turn a gearbox assembly, which in turn drives the propellers. Well, the final decision was to go straight to a pure jet, and the result of that was an all-jet version of the airplane.
With the dawn of the jet age, Northrop's engine problems became a thing of the past. 2 of the XB-35 airframes were redesigned and fitted with 8 Allison J-35 jet engines. The updated aircraft was designated the YB-49.
The B-49, as a jet-powered airplane was designated, was essentially the identical airplane to the B-35 except for the power plants and for the installation of 4 small vertical fins. These were to provide an element of directional stability that was previously provided by the propellers and the propeller housing shafts.
With the move to jet power, everything changed. 8 Allison J-35 motors, eliminating the complex drive systems and the vibration that had plagued the YB-35. The YB-49 look was just cleaner. It'd be faster and far closer to what Northrop had envisioned from the beginning. A true flying wing, now powered by the technology it had been waiting for. At the controls, test pilot Max Stanley, one of Northrop's most experienced pilots, tasked with bringing the jet-powered flying wing to life. On October 22, 1947, the YB-49 made its first flight, setting off from Northrop's airfield in Hawthorne, California. Almost immediately, it proved more promising than its piston-powered predecessor. At last, Northrop's ambitious flying wing was back on track, for now.
The B-49 was an absolute joy to fly. And it was my first experience. As a matter of fact, it was the first experience of most people for a jet, flying in a jet airplane that was large, roomy, marvelous performance, very quiet, very smooth, and it was so much superior in every regard to the propeller airplanes that there just is no comparison.
After its initial flights, the YB-49 was sent to Muroc Dry Lake for Air Force pilots to begin testing. Among those assigned, Major Robert Cardenas. At altitude, the aircraft showed real promise. In one test, it remained above 40,000 feet for more than 6.5 hours, an unofficial endurance record. But Cardenas had concerns. At the edge of its performance envelope, he thought the plane behaved unpredictably, even rotating backwards in a stall. It was a warning he passed along to a new arrival in the program, test pilot Glen Edwards. Northrop would later dispute those concerns, insisting such behavior was impossible in a flying wing. But when Glen Edwards joined the program in 1948, he too began to show some concerns. After just a few flights, he wasn't convinced. In his diary, he described it as, quote, the darndest airplane I've ever tried to do anything with. At times, quite uncontrollable. On June 5th, 1948, during a test flight over the desert, the aircraft entered a planned maneuver, part of an evaluation of stall recovery. Then suddenly, it pitched over into a steep, high-speed dive. As it turns out, the loads on the airframe increased beyond what the structure could handle. Both outer wing sections had torn away from the center section. The aircraft had broken apart in midair. All 5 crew members were lost. In spite of the tragedy, Northrop's beleaguered flying wing program continued moving forward. In the air, the YB-49 continued to demonstrate flashes of brilliance. Fast, smooth, and unlike anything else in the sky. Even its shape reduced its radar signature, a detail not fully appreciated at the time. In February of 1949, it flew from California to Washington, D.C. in just over 4 hours, a remarkable achievement. But behind the headlines, problems remained. On the return flight, multiple engines had to be shut down, raising new concerns about reliability. And in testing, other limitations became clear. The aircraft had a tendency to drift in yaw, especially in turns or turbulent air. Engineers worked to correct this. New autopilot systems designed to stabilize the aircraft and damp out those oscillations, promising improvements, but not a complete solution. At the same time, jet power had brought its own trade-offs. Fuel consumption increased, cutting the aircraft's range nearly in half from the YB-35. In a Cold War, where penetrating deep inside the vast Soviet Union was critical, this was a problem. Meanwhile, more conventional designs were proving faster and better suited for the evolving demands of high-altitude, long-range strategic bombing. Despite early interest and even plans for production variants, the future of the flying wing grew uncertain. And yet, for many, the idea still held enormous promise. Not just as a bomber, but something else. A radically different version of flight, one that some believed could shape the future of air travel.
Now, a preview of the flying wing transport of tomorrow. The midsection provides ample room for 80 passengers. Spaciousness keynotes the luxurious main lounge, extending 53 feet inside the wing. And future air travelers will really see something. Through the plexiglass windows of the front wing edge, passengers have an unimpaired view of the Earth unrolling thousands of feet below. Coast-to-coast flights in 4 hours may not be too far away. The dorsal tip of the plane provides an excellent vantage point to see the world go by. Snug as bugs in their magic carpet, air travelers can look down on mere Earthlings as the double quartet of mighty turbojets whistle them through space. The sleek air Leviathan carries more cargo farther, faster, and with less fuel than any comparable plane. And the bar will raise the spirits of those who don't feel high enough in the stratosphere. The flying wing has the stability of a fine club. The public quickly accepts all the miracles that science provides. Even skyliners like this will become commonplace. But the giant flying wing is more than a super streamlined airplane. It is the fulfillment of scientific vision and symbolizes the practical dreams of science for our world of tomorrow.
The YB-49 would never carry passengers, and the dream of flying wing airliners has yet to be realized. But for a brief moment, the flying wing had arrived. Fast, elegant, and unlike anything else in the sky. A vision of the future, already in flight. And yet, even as it reached its peak, the program was coming to an end. In early 1950, the remaining aircraft still under development were ordered scrapped. Flight testing ended in March. Just days later, the program was canceled. For Jack Northrop, the flying wing was never just an airplane. It was a lifelong pursuit, an idea he carried from his earliest days in aviation. From the first experiments, to the N1M, to the YB-35 and the YB-49, each was a step towards the same goal. But during his career, he would never see that vision fully realized. The aircraft were gone, the program ended, and the idea set aside. In 1976, with his health failing, Northrop reached out to NASA, hoping the idea hadn't been forgotten. NASA's reply was simple. The concept still had merit. Then, close to the end of his life, he was shown something remarkable. A scale model of a new aircraft. The B-2 Spirit. The man with a dream was finally able to look upon the realization of his life's work. 10 months later, Jack Northrop was gone, but his idea was not. The flying wing, once dismissed, dismantled, and nearly forgotten, had returned. Not just as a dream, but as the future of flight.
Let's take a look at how the magnificent Northrop XB-35 flying wing was made. The first flying wing bomber, and the largest flying wing ever constructed, is approximately 75% complete at the Northrop plant, Hawthorne, California. The wingspan of the XB-35 is 172 feet. At the center section, the wing chord is approximately 37 feet, tapering to 9.5-foot wingtips. Design gross weight is 155,000 pounds. Maximum allowable gross weight is 208,000 pounds. The airfoil is an NACA laminar flow section. Internal structure is conventional riveted construction with variations as required by the aircraft's unusual configuration. Because of the airplane's huge size, transits mounted on permanent leveling pads on the jigs are used to accurately locate major structural members. 75S high-strength aluminum alloy is used in main structural members to reduce weight. There are 8 bomb bays capable of housing a total maximum bomb load of 51,000 pounds. Bomb bay number 4 may be entered from the crew compartment and serves as an emergency exit. Thickness of this flying wing at the center section is 7 feet, providing ample room for the crew to walk upright. Oil coolers, intercoolers, turbo superchargers, and heat exchangers are housed in the plenum chambers forward of the front spar. Formation of ice on the wing is prevented by heated air passing through ducts in the leading edge. The largest free-blown plexiglass canopy ever constructed will cover this opening, and provide visibility for the pilot and forward gunner. The workman is entering through the bombardier sighting panel. Total built-in fuel capacity is 10,000 gallons, more than the standard railroad tank car. An additional tank car of fuel can be carried in droppable bomb bay tanks. This tremendous fuel capacity gives the XB-35 a maximum estimated ferry range of 12,000 miles. Landing gear is conventional tricycle arrangement, with the nose gear retracting sideways into the wheel well. The plane is powered by 4 Pratt & Whitney Wasp major engines. These R4360 engines are completely housed within the wing and are capable of developing a total of 12,000 takeoff horsepower. 15-foot, dual, contra-rotating pusher props will drive the XB-35 at an estimated 390 miles per hour at 35,000 feet. It is estimated that the XB-35 will fly by the end of 1945.
4-ship formation coming in over the field, being led by the B-49, B-47, 45, and the F-86. Now the flying wing, B-49. B-49. The B-49.
Today's basic aircraft design still has unnecessarily large drag forces. We now have an airplane which, due to its increased efficiency, is capable of transporting a given load 25% farther or faster than is possible with an ordinary airplane using the same power.
The B-2 Spirit takes the shape of a flying wing, serving as a strategic bomber. Its streamlined and efficient design makes it nearly undetectable by enemy radar. Despite being one of the most sophisticated weapons in America's arsenal, its journey to deployment was nearly jeopardized. Jack Northrop, an aviation legend, conceived the idea of the flying wing, turning his inspiration into an all-consuming obsession. When persistent design issues led the military to discard his prototype as scrap metal, Jack Northrop retired, deeply disheartened. Nevertheless, the vision of the flying wing that he passionately pursued persists. Featuring a striking black wedge shape spanning 172 feet from wingtip to wingtip, the B-2 Spirit resembles a futuristic bird of prey more than any other human-made object in the sky. It boasts an impressive payload capacity of 40,000 pounds, capable of carrying conventional or nuclear weapons to any target worldwide. Its unique ability to attack with pinpoint accuracy while maintaining near invisibility to enemy radar sets it apart. This revolutionary aircraft stands as the latest addition to a lineage of U.S. nuclear intercontinental bombers dating back to the Cold War's inception in the late 1940s. The B-36 Peacemaker, the initial and largest among these planes, was chosen for production over the direct predecessor of the B-2, the YB-49. The narrative of these two aircraft, one colossal and conventional, the other sleek and a flying wing, is steeped in competition, controversy, dreams, and disappointments, reflecting the vision of a pioneering aviator who envisioned the flying wing as the shape of the future. The visionary figure was none other than Jack Northrop. Jack Northrop firmly believed in the principle that if something is both efficient and beautiful, it is right. This philosophy infused a sense of velocity into every aircraft he designed. Commencing his career at Lockheed in 1919, Jack Northrop's passion for creating the perfect airplane led him through pivotal roles at Douglas, Boeing, and eventually his own company.
His peers respected him and considered him one of the design geniuses of American aviation. Donald Douglas mentioned that there's a little bit of Jack Northrop in every American airplane that's been designed.
When you walk around the United States Air Force Museum, you see the little influences of Northrop. You can actually see the imprint of the man's work. We have an A-17, and his name is just stamped all over this aircraft. It's a gorgeous airplane to begin with, and it shows a certain degree of sophistication that some of the other designers weren't quite there yet.
One of Northrop's groundbreaking contributions to aircraft design was the introduction of the all-metal monocoque fuselage. This innovation eliminated the need for drag-inducing wing supports like struts and wires.
We have in our collection a Northrop Alpha, and it was the first monocoque aircraft built by Northrop. It was very unique. It was used for carrying passengers like an airliner. And then later on, when what they call a CAA said that we needed a multi-engine aircraft for airliners, it was relegated to carrying the mail. All-metal, monocoque structured airplane, very well built.
In the 1920s, Northrop Company played a pivotal role in designing the Spirit of St. Louis for Charles Lindbergh. Additionally, they crafted the first all-metal low-wing fighters for both the Navy and Army Air Corps. Northrop's influence extended to the design of the Lockheed Vega, a highly successful aircraft flown by aviation pioneers Wiley Post and Amelia Earhart in the 1930s. The profits from this venture fueled his ambition to pursue a project he had dreamed of since adolescence, the flying wing. The flying wing concept, ingrained in nature itself, is a timeless design observed in various forms, from birds and sea animals to wind-borne seeds. Some aviation pioneers of the early 20th century were inspired by these examples, designing flying machines that attempted to emulate the wing-like aerodynamic shapes they observed in the natural world. Jack Northrop's fascination with the shapes of nature was deeply rooted in his upbringing in Santa Barbara, California. Observing the graceful soaring of seagulls above the local beaches inspired him to delve into the study of flight. During this time, he began sketching airplane designs, predominantly centered around one large wing. Aligned with the ideas of his predecessors, Northrop envisioned that such an aircraft, characterized by a prominent wing, could be significantly lighter and more efficient than traditional designs.
It's aerodynamically sounder. You don't need a stabilizer. You don't need the tail. You do not need a long fuselage, which all of these increase drag. More drag means you have to have more fuel to fly further distances.
However, the early wing design encountered challenges related to control and stability. Undeterred, Jack Northrop remained enthralled by the potential advantages of the flying wing. From the outset of his career, he committed himself to addressing the drawbacks associated with wing-only designs.
He worked for Lockheed and Douglas before he founded his own company, and of course at lunchtime the engineers would get together and have a little bull session, and they all kind of agreed that the flying wing was the ultimate design.
After conducting experiments with the gliders, Northrop, in 1929, reached a milestone by testing a powered prototype of a flying wing. Due to the uncertainties surrounding the aerodynamic stability of a pure flying wing, this design incorporated some features reminiscent of a conventional aircraft.
It did have twin tail booms with a conventional tail in the back. He was trying to get the best lift coefficients on the wing roots and airfoils, and he learned a lot from that.
In the fall of 1939, when Germany invaded Poland, Northrop formed his own company, Northrop Aircraft, and began producing new aircraft and bombers for the U.S. and its allies. Simultaneously, Jack Northrop embarked on drafting plans for an innovative flying wing, envisioning a design where all control surfaces, including the rudders, were integrated into the trailing edge. This revolutionary approach aimed to eliminate the traditional tail, resulting in a pure flying wing. By the summer of 1940, Jack Northrop and his design team initiated test flights for their groundbreaking prototype, the N1M, conducted on the deserted dry lake bed known as Muroc Army Airfield, just north of Los Angeles. Similar to Northrop's 1929 wing, the N1M prototype faced challenges.
It was very underpowered. When they flew it out of Hawthorne, they wanted to move it to Edwards, which was Muroc at that time. They towed it over the hill with a DC-3. Didn't have the power to get over the hills. Well, it was the first successful wing. I don't know for what period of time they flew it, but it's now in the Smithsonian.
Despite the installation of a more suitable engine, the aircraft underwent 200 test flights at Muroc. Throughout this period, Northrop tirelessly sought solutions to the inherent stability issues prevalent in Tailless aircraft designs. The quest for an optimal solution to control the phenomenon known as yaw presented the most formidable challenge.
Yaw is your left and right, where the airplane tends to yaw about its vertical axis. On a conventional airplane, this is controlled by rudder. On a winged vehicle, you have to have some device that creates drag at the wingtip to control or create yaw.
In 1941, General Hap Arnold, the commander of the U.S. Army Air Corps, took the notice of Northrop's N1M. Arnold, actively searching for a new bomber capable of reaching Germany from the United States, recognized the strategic importance of such an aircraft. Although the United States had not yet declared war against Germany and Japan, the escalating concerns about Nazi Germany's successful air campaign against Britain raised the possibility of the Allies lacking secure air bases in Europe.
In 1940, when it was obvious that the British were in serious trouble and they may fall, leaving just the United States to stand against Nazi Germany and the Axis powers, the Army Air Corps started looking for a super long-range bomber to be able to strike targets in Europe from continental United States.
The Army Air Corps issued a request for designs, specifically seeking a high-altitude bomber capable of carrying 10,000 pounds of bombs to its target and returning home, covering a total distance of 10,000 miles. Impressed by what he observed during a visit to Northrop at Muroc Field, General Hap Arnold, on November 22, 1941, signed a contract with Northrop to further develop his flying wing bomber, the N1M.
It offered the possibility of ultra-long range. The flying wing was becoming more and more recognized as advanced. The aerodynamic aspects of it were quite evident, and the long range because of the low drag induced by the aircraft itself. Plus, we had to start thinking very progressively. We couldn't think of just a regular aircraft to get across the continental United States or across the North Atlantic or anywhere in the world.
Just 2 weeks later, on December 7, 1941, Japan bombed Pearl Harbor, propelling America into a global war. In this tumultuous period, Jack Northrop's dream of seeing the flying wing enter large-scale production seemed on the brink of realization. The surprise attack on Pearl Harbor prompted the United States to declare war against the Axis powers and injected a renewed sense of urgency into the development of Jack Northrop's flying wing superbomber, the B-35. To hasten the testing of the design, the Army allocated funds for the construction of experimental prototype versions, which were 1/3 the size of the B-35, reflecting the nation's determination to expedite the development of advanced aircraft during this critical time in history. Looking like something out of a Buck Rogers matinee, these aircraft, with the designation N9M, first took flight in December 1942. The fully restored N9MB, currently the sole flying example, occasionally graces the skies near its home at the Planes of Fame Museum in Chino, California.
The wingspan of the B-35 was 179 feet. This is roughly 60 feet. So it's 1/3 scale, same airfoil, same sweep, same dihedral, just scaled 1/3. The thrust center line of the two engines replicates the center line thrust of the four engines on the B-35, and the thrust to weight ratio is roughly the same.
Among its numerous innovations, the Northrop N9M holds the distinction of being the first aircraft equipped with hydraulically boosted flight controls. The wing itself featured groundbreaking control surfaces, with Northrop ingeniously combining the functions of the aileron and elevator into a single component called an elevon.
This is your primary pitch and roll control. That is, if they both go up and down, you get a pitch input, and if they're differential, you get a roll input. It's where you bank. Out here is the rudder, which is a drag device. It splits, it creates a drag on the wingtip.
Normal airplane has a rudder at the back of the airplane, if you recall, on a fuselage for directional turns and so forth. So he had to basically invent how he would actually steer or fly the airplane.
To address the absence of a traditional tail, the N9M's design incorporated elevons, creating a distinctive flying experience for its pilots. This uniqueness remains evident in today's aviation landscape.
Flies very well once you get used to it. Not difficult, just different. It's very meaningful to fly this. Certainly it would be to anybody that would have that opportunity. It's a very historic airplane, and once you see it fly, you understand why.
However, concurrently with Jack Northrop's endeavors in developing the flying wing bomber, a formidable competitor was also taking shape, the Convair B-36. It was developed by a group of engineers, including Robert Whitmer.
I got involved with the B-36 in order to run the first wind tunnel test, subsonic wind tunnel test, which was to be run at MIT. And I was asked to run that program.
The B-36 emerged in response to the same Army Air Corps requirement for a bomber with the 10,000-mile range and 10,000-pound payload. However, it stood in stark contrast to Jack Northrop's vision of beauty and efficiency embodied in the flying wing. In essence, the B-36 adopted a completely conventional design, diverging sharply from Northrop's aesthetic preferences. Its distinguishing feature was its sheer size, an unparalleled enormity in the history of aviation. The B-36 boasted a wingspan of 230 feet, surpassing the Wright brothers' inaugural flight at Kitty Hawk, North Carolina, by over 100 feet.
The aircraft was going to be so large, they had to save weight any way they could. So it meant using new tanks to hold new types of gases to be used for fire extinguishers on the engine. Something as simple as that sounding takes quite a bit of effort. You have to have new engines willing to pull this aircraft, or push it, as it turns out, for 2 days essentially on a mission and not stop.
This colossal aircraft overshadowed Northrop's B-35 design in every aspect, notably in the range and payload. Despite its impressive dimensions, the B-36 faced developmental challenges of its own. Consequently, the Army Air Corps chose to persist with Northrop's flying wing, recognizing its potential.
In case one failed, the other was there. And when you're talking about national survival, having a second option, even if it's expensive, the treasure needs to be spent to save the blood of the Republic later. And that's what they were doing. So it gave a fallback option.
As Jack Northrop continued refining his work on the B-35 bomber, he simultaneously delved deeper into exploring the possibilities and capabilities inherent in the flying wing concept.
Northrop also designed several flying wing fighters. I'm thinking of the P-79B flying ram, powered by twin Westinghouse turbojets. And it was a rather unique aircraft, and unfortunately, the war ended, they didn't do much with it.
Northrop also built the MX-334 rocket wing fighter, America's first rocket-powered airplane, and the piston-powered XP-56 Black Bullet. Despite their promise, both the flying wing bomber and the B-36 encountered substantial development issues and never transitioned into full-scale production. In 1944, as focus shifted towards the larger and more heavily payloaded B-36, the Army reconsidered the future of the B-35. Rather than pursuing its role as a heavy bomber, the Army envisioned the B-35 as a potential experimental medium-range bomber and reconnaissance aircraft. The urgency for such craft diminished with the non-occurrence of the potential crisis that had initially spurred the development of the flying wing bomber and the B-36, the fall of Britain. The heavy bomber role within the U.S. Air Force was, in the meantime, fulfilled by a series of other aircraft such as the B-17 Flying Fortress, the B-24 Liberator, and the B-29 Superfortress, none of which were connected to Jack Northrop. In August 1945, one of the war's concluding acts saw the B-29 named Enola Gay, piloted by Colonel Paul W. Tibbets, dropping the first atomic bomb on Hiroshima. 3 days later, another B-29 targeted Nagasaki with a second atomic bomb. These events underscored the immense power wielded by bomber aircraft in the nuclear role. With the distant Soviet Union emerging as America's likely adversary in the post-war era, the urgent need for a new long-range heavy payload bomber became more apparent than ever.
What the atomic bomb does for air power is, for the first time, aviators can do what they say they can do. They can take out a strategic target, because now they don't have to send 1,000 planes across to do one job and go back. Now, one aircraft, one bomb, can take out an entire industrial complex or an entire city if it's necessary to do so.
The geopolitical landscape and advent of nuclear capabilities elevated the importance of advanced bomber aircraft for strategic purposes. Partly for this reason, development efforts on Jack Northrop's B-35 as a potential long-range nuclear bomber continued. In June 1946, almost a year after the war's end, Northrop's B-35 finally took flight. Measuring an impressive 172 feet from wingtip to wingtip, the B-35 was equipped with 4 robust 12,000 horsepower piston engines, each driving a pair of counter-rotating pusher propellers. The aircraft's 9-man crew included 3 gunners responsible for defending the plane with 50 caliber machine guns and remotely controlled barbettes. Despite the aircraft's futuristic appearance, the wing design presented challenges for Jack Northrop.
Jack Northrop had just a run of bad luck. The first aircraft crashed before he could draw the technical data that he needed from that aircraft, so he had to proceed with the second prototype. Without the necessary information that he would have garnered from the first one, it put the aircraft at a great disadvantage.
While he had successfully overcome various design obstacles, finding a viable solution to the problem of yawing proved elusive. The B-35 also grappled with issues such as overheating engines and gear shift vibration. Faced with these challenges, Northrop decided to integrate a new technology into the wing, turbojets. By this time, turbojets had become the preferred propulsion method for all new military aircraft. Experimental versions of the wings were outfitted with 8 turbojet engines, leading to its redesignation as the YB-49. The introduction of jet propulsion brought a transformative improvement in performance, swiftly resolving developmental problems like gear shaft vibration. Some test pilots even reported that the wings exhibited flight characteristics more reminiscent of a fighter than a traditional bomber, highlighting the positive impact of the shift to jet technology. At Northrop's suggestion, test pilot Robert Cardenas demonstrated the wing speed by undertaking a cross-country flight.
At an official speed record from Edwards all the way back to Andrews Air Force Base, showed it off to President Truman, and Truman went through the airplane and saw it flying, and he thought we ought to buy some of these.
The transition to larger jet engines on the YB-49 posed significant challenges, as it reduced the wing's bomb capability precisely when a much larger payload and range, akin to that of the B-36, were needed to transport the massive and heavy atomic bombs in use at the time all the way to the Soviet Union. Furthermore, Jack Northrop's wings still grappled with serious stability issues. On June 5, 1948, during a series of stall tests on the YB-49, Danny Forbes and Major Glen Edwards were at the controls. The night before, Edwards had expressed optimism about the wing's progress, noting its impressive performance despite numerous test flights and extensive flying hours. However, he acknowledged that the stability remained a significant problem, adding, "But the plane goes like hell." Tragically, during the tests that day, the pilot lost control of the aircraft, resulting in a crash and fire that claimed the lives of all 5 crew members. In honor of Major Glen Edwards, the base at Merak was renamed Edwards Air Force Base when the U.S. Air Force was officially established as a separate military branch. This renaming commemorated the sacrifice of those involved in advancing aviation and aeronautical innovation. Fearing that his beloved flying wing was doomed as a military project because of high-profile failures like the Glen Edwards crash, Jack Northrop launched a publicity campaign promoting the flying wing as the airliner of tomorrow.
Now a preview of the flying wing transport of tomorrow. The midsection provides ample room for 80 passengers. Spaciousness keynotes the luxurious main lounge, extending 53 feet inside the wing. And future air travelers will really see something. Through the plexiglass windows of the front wing edge, passengers have an unimpaired view of the Earth unrolling thousands of feet below. Coast-to-coast flights in 4 hours may not be too far away.
Despite earnest efforts, no civilian air service expressed interest in the flying wing, leading to the U.S. Air Force's decision to cancel Northrop's contract in 1948. Instead, they opted to proceed with the Convair B-36. The cancellation of the flying wing project remains a contentious decision, with accusations of political bias favoring Convair mingling with the concerns about issues with the YB-49. Critics argued that political considerations played a role in the decision-making process, but undeniable were the significant stability problems inherent in the flying wing design. Many viewed the YB-49 as unstable both as a bombing platform and a long-range reconnaissance aircraft.
It was understood by the Air Force at the time, even when they canceled the program. It had great potentials, but not quite now. Maybe someday in the future.
For Jack Northrop, the most devastating blow came when the Air Force ordered the destruction of all existing flying wings, melting them down into aluminum ingots.
It was devastating. Come in and see strangers come in and cut up your product right in front of your employees. It was really disheartening, of course.
This experience deeply disturbed Northrop, prompting him to leave his company and take an early retirement, completely withdrawn from the aviation industry. In the race to be armed and ready for the Cold War, the B-36 emerged victorious over the flying wing. For the next decade, the B-36's colossal presence dominated the skies, serving as the backbone for America's nuclear arsenal. On December 7, 1948, exactly 7 years after the Japanese attack on Pearl Harbor, a giant silver bird with 6 pusher-type props departed from Carswell Air Force Base, Texas. Over the Pacific, near Hawaii, it opened its bomb bay doors and dropped a payload of 10,000 pounds of dummy bombs into the ocean, symbolizing the era of strategic air power during the Cold War. This airplane was the Convair B-36, and it had demonstrated, among other things, that it was a true intercontinental bomber capable of striking at almost any target in the world. The B-36 embarked on a long and challenging journey, marked by disappointments, delays, and intense controversy from its inception on the drawing board to its eventual operational status.
It was a disaster. We needed to change the wing, and I knew we had to change the control surfaces. We had to put a different kind of fan on because it's a pusher engine to cool the things on the ground statically when it's not moving. The whole airplane had to be totally redesigned here. And we did that.
One pivotal element in the final decision to proceed with the troubled project was the escalating tensions of the Cold War. Air Force Secretary Stuart Symington, recognizing the B-36 as the sole bomber capable of reaching targets inside the Soviet Union, played a crucial role in the program's continuation. The Strategic Air Command, or SAC, led by General Curtis LeMay, emerged as the primary custodian of U.S. nuclear weapons, and the B-36 became the cornerstone of U.S. Cold War strategy.
It was the main part of Strategic Air Command. It was General Curtis E. LeMay's big stick. We flew everywhere, made lots of noise. Of course, there was a big battle going on, whether you should get aircraft carriers or you should get B-36s. And at that time, the B-36 won.
The logistical challenge of finding a sufficiently large facility to assemble the colossal B-36 was formidable.
Do you have floor space to build this monster? It's huge. You need a big hangar to put it in, to build it in. So where do you build it? You have to go to Fort Worth, where they just happen to have a large enough facility, and it's all enclosed so people can't peek in the windows.
The mile-long facility in Fort Worth, Texas, originally constructed for assembling B-24 bombers during World War II, stood as the only building on the planet spacious enough to accommodate the gigantic B-36. In the air, the B-36, often referred to as the Big Stick, boasted an extraordinary fuel capacity, enabling it to remain airborne for 2 days, far surpassing any other bomber in history. Additionally, it was the sole aircraft capable of carrying the exceptionally large and heavy nuclear weapons in the U.S. arsenal at the time.
People often ask, why did the B-36 have to be so large? Well, it had to carry a lot of fuel to fly long range, but it also had to have a massive bomb bay to carry the large thermonuclear weapons like on either side of the bomb bay. These are massive monsters, and it requires a massive bomb bay to carry them.
With 4 bomb bays, each with a capacity of 3 freight cars, the B-36 could carry a maximum payload of 84,000 pounds, exceeding the gross weight of the B-29. The B-36 thus represented a formidable and unprecedented force during this critical period of Cold War military strategy.
One of the biggest problems was building the frame to build the aircraft. They finally brought in a bridge builder, and he designed what we called a K-type frame that actually was a basic strength holding the fuselage together.
Designing adequate landing gear for the 210-ton plane also posed unique problems.
When it was first designed, the B-36 wheel was the largest aircraft tire in existence in the United States at the time. This had problems. First, the weight of the wheel itself. It could push through any concrete runway at the time, except for a very few within the United States. The planners came up with a 4-wheel design, like on a B-36 that you'll see over here. This aircraft had 4 wheels. First, it lowers the risk if one tire goes out, the plane won't crash on takeoff or landing. Also, by spreading the weight out over 4 tires, it increased the number of runways that the B-36 could operate with.
The original design of the B-36 featured 6 28-cylinder, 4,360 cubic inch turbo-supercharged radial engines, each rated at 3,500 horsepower. However, reaching the promised service ceiling of 40,000 feet posed a formidable challenge, and the top speed of the bomber barely reached 230 miles an hour. Critics raised concerns about the B-36's vulnerability to enemy fighters, particularly the new Soviet MiG-15. The slow-flying bomber was considered by some as a sitting duck, leading to accusations of being a billion-dollar boondoggle. In 1950, congressional hearings were held, sparkling a scandal known as the B-36 affair. Both Convair and the U.S. Air Force underwent an investigation. The controversy further intensified as part of the heated debate between the Air Force and the Navy over which service should control the U.S. nuclear mission in 1951. Efforts to address some of the B-36's issues led to modifications in the form of adding a pair of J-47 turbojet engines under each wing, employing the slogan 4 burning and 6 turning. This modification significantly improved the Big Stick's performance, boosting its top speed to over 400 miles an hour and nearly doubling its rate of climb. With these enhancements, the modified B-36 could operate at higher altitudes than most fighters in the thin atmosphere at those elevations, offering an improved and more formidable version of the aircraft.
Some F-100s challenged us, and they were pretty braggadocio about how their airplanes can fly compared to this old hunk of metal here. 4 of them came in on us into a sharp turn. The guys that turned with us all stalled out and went down a little bit and didn't get us.
The B-36 featured retractable, remotely fired turrets with 20mm cannons located at the top, bottom, front, and rear of the aircraft, establishing it as the more heavily defended bomber in existence.
We were quite well protected if we had fighters coming in on us. We could put a good screen of lead out there.
A distinctive and unique feature of the B-36 was the pressurized tube light passageway, serving as a walkway to move between the front of the airplane and the crew compartment in the rear.
The tube was an 80-foot tube from the forward pressurized compartment to the aft pressurized compartment, and it had a little cart like one of these carts you would lie on working underneath a car. And you would get in there and grab a cable in there and then go to the aft compartment. There were doors on both ends so that if one compartment depressurized, you wouldn't be shot out like a cannon.
Despite its ongoing controversy surrounding the giant bomber, the Convair B-36 effectively fulfilled its role as a deterrent to nuclear war from 1949 to 1959.
At the very time when the American people are most nervous, all of a sudden you have this massive, huge, comforting aircraft. It gives the American people a sense of security that allowed us to think things through more clearly, come to rational decisions. So it's a security blanket for the American people, as well as a deterrent to the Soviets.
In 1959, after a decade of service, the B-36 was replaced by the new jet-powered B-52 Stratofortress, another colossal conventional aircraft design. With Jack Northrop in retirement and no other flying wings in development, it seemed like the aeronautical world had moved beyond his dream. It would take nearly 30 years before an aircraft with a strangely familiar shape returned like a boomerang to replace the B-52, the B-2. During the test flights of Jack Northrop's flying wing bomber, one of the surprising outcomes was the difficulty Air Force personnel encountered in trying to track the plane on radar. showcasing the aircraft's advanced stealth capabilities. The B-2, inheriting the legacy of the flying wing, would go on to redefine strategic bomber capabilities with its stealth technology. The most important reason for this was its shape. The elegance and economy of the wing's design meant that it had fewer surfaces to reflect a radar signal back to an enemy receiver than a conventional aircraft. The characteristics of the flying wing, particularly its difficulty to detect on radar, foreshadowed the development of stealth technology.
The advantage of using a stealth technology is that you can use this one aircraft to fly in and you can deliver a precision-guided weapon at your leisure. You don't have to worry nearly as much about enemy air defenses. They have to worry about you instead.
The quest for stealth technology emerged almost immediately after the introduction of radar during World War II. As radar became a ubiquitous element of warfare, efforts were initiated to find ways to deceive it. Early attempts involved jamming German radar with clouds of tinfoil strips, codenamed Window, which proved highly successful. However, little progress was made in the realm of making aircraft themselves less detectable. The inadvertent success of the flying wing in evading radar detection laid the foundation for the deliberate incorporation of stealth technology in subsequent aircraft. The SR-71 and the B-1 bomber were among the first U.S. aircraft to purposefully integrate stealth technology, although it was still in its early stages of development. Interestingly, the advantages in stealth demonstrated by the flying wings seemed to be overlooked following the cancellation of the program. It wasn't until the 1970s, with the Soviet air defense network becoming more formidable, that research on stealth design gained renewed impetus. Operating in secrecy, designers developed several prototypes, ultimately leading to the creation of the F-117 stealth fighter. Characterized by its heavily faceted shape, the F-117 reflects radar signals away from enemy receivers, making a significant leap forward in the evolution of stealth technology. The flying wing's early contributions to radar evasion became a critical foundation for the advancements that would follow in the realm of stealth aircraft design. But other scientists at Northrop Aircraft, working on an unrelated project in the early 1960s, had determined that the ideal shape for a stealth plane was actually far different than the angular form of the F-117.
We had a small group of what we called phenomenologists at the time. They were basically physicists and very bright young people with a wide open mind who became curious about why is it that we can see things on radar? Is there a way of having a shaping that would make it difficult to see? They came up with these shapes, and we were startled and pleased because, lo and behold, the shape they came up with was exactly the shape of a flying wing.
In the early 1970s, top-secret development commenced on what would eventually become the B-2 flying wing stealth bomber, designed to serve as America's next-generation nuclear transcontinental heavy bomber.
Essentially, it needed to be, number one, stealthy for future technologies and future enemy radar systems. It needed to have a large payload capacity. Thirdly, it needed to be precise. Lastly, it needed long range, intercontinental.
Similar to the challenges faced by the YB-49 and B-36, overcoming technological problems was just one aspect of the difficulties encountered during the development of the stealth bomber. Initiated during President Carter's administration, the B-2 project faced cancellation in the early days of President Reagan's first term, only to later be revived. Despite controversy, significant technical challenges, and substantial cost overruns, the development of the aircraft persisted. In the spring of 1980, an ailing and wheelchair-bound Jack Northrop visited the Northrop plant, where he was shown models for the future B-2 bomber. Notably, the B-2 was planned to have a wingspan of 172 feet, identical to Northrop's B-35 and YB-49. Touched by the experience, Northrop, who had less than a year to live, expressed, "Now I know why God has kept me alive the last 25 years." 8 years later, on November 22, 1988, the first B-2 Spirit was unveiled at the Northrop Site 4 facility in Palmdale, California. During the event, as the doors opened, Northrop President and CEO Thomas Jones made a spontaneous announcement, marking a significant milestone in the realization of Jack Northrop's enduring vision.
I was standing there, and obviously you get overcome by things, and you see this beautiful airplane come out, and you see this great crowd of people, and so on, and just said, "Jack Northrop, we salute you," which we all said.
The development of computer-assisted fly-by-wire flight controls, which were already being used by the F-117 and other advanced military aircraft, meant that the stability problems which had plagued Northrop's flying wing were no longer an issue in the stealth bomber.
The yaw developed as an inherent trait with a flying wing. What allows us to solve that problem now is the flight control computers are so fast that they're able to make the flight controls move fast enough that it stops that yawing from occurring. Conventional airplanes, early on, you physically would pull on the control stick, and it would move a series of cables and bellows and pulleys to make it all work. What fly-by-wire now does for us is allows the pilot to move the stick, and now computers take care of all that mechanical control, and it sends a computer signal out, just like calling on a telephone.
The aerodynamic efficiency inherent in Northrop's flying wing design paid dividends in the B-2 by allowing its engines to operate at lower power settings, contributing to a quieter operation of the aircraft. Notably, the grandson of the pilot who flew Enola Gay on the world's first nuclear mission is one of the pilots of these remarkable aircraft.
When you look at it, you don't really see any engines. You see a couple of small intake holes on the front, a couple of small exhaust holes on the back, and that's about it. All of that works together to help reduce the signature and make the airplane more stealthy.
Another key factor in the B-2's stealth compatibilities lies in the use of graphite composite material, which effectively absorbs radar energy. Maintaining a completely smooth surface on the airplane is also crucial in achieving optimal stealth characteristics.
With this aircraft, you have to be more careful not to scratch the paint and the surfaces and flight control surfaces. If I bump this graph with a stand, I'm liable to do anywhere from 30 to 40 hours worth of damage on a small scratch. With that paint missing, it's liable to get the radar-absorbent and possibly point your position out to who's ever trying to track you.
These qualities collectively contribute to the B-2's remarkable success in the realm of stealth, providing it with the radar reflectivity equivalent to that of a basketball. Despite the challenges faced during its journey to production, the B-2 bomber had become the cornerstone of America's nuclear bomber force. However, its initial deployment in combat did not involve a centerpiece role in an atomic superpower showdown, but rather in a more conventional foreign conflict. In the early morning hours of March 24, 1999, two B-2 stealth bombers took off from their base at Whiteman Air Force Base, Missouri, marking a significant moment in the operational history of the B-2 in a more conventional military context. They crossed the North American continent, then the Atlantic, en route to targeted facilities in the former Yugoslavia.
I was going into my first mission, and I had stealthed up. When the controller came back to me, he said, "I've lost you on radar." And I tell you, that was just like a warm, fuzzy, reassuring feeling. Gave you goose pimples like, hey, this actually does work.
Approaching their targets with precision, the B-2 stealth bombers utilized their launch and leave capabilities during this crisis in Kosovo, successfully deploying 30 2,000-pound satellite-guided smart bombs. These smart bombs were designed to land within 30 feet of their programmed coordinates, showcasing the B-2's accuracy in delivering payloads.
When my weapons bay doors opened and the weapons started coming out, those 2,000-pounders coming out just shuttered the airplane. Don't, don't. That's when the reality of what we actually were doing really hit pretty hard. And we started to see surface-to-air missiles being shot. It started just sinking in that, hey, this is for real.
After dropping their bombs, the bombers returned to Whiteman Air Force Base approximately 31 hours after takeoff. Notably, the B-2s executed their missions in a manner that often left the enemy unaware of their presence overhead. A highlight of the stealth bombers' weaponry during the Kosovo crisis was the deployment of the Joint Direct Attack munitions. JDAM transformed unguided bombs into highly precise weapons, contributing to the success of the B-2 in the 78-day air campaign.
We strapped on a tail kit. It has fins that move, and these GPS satellites, the global positioning system, feeds it current information, updating it all the time, all the way down until it strikes the target.
Throughout the campaign, B-2 Spirits flew 49 missions, with all aircraft and their crews performing flawlessly, marking an impressive combat debut for the Flying Wing stealth bomber.
49 for 49 on-town takeoffs, done with only 6 aircraft at the time. That's all we had here on this base. That's an amazing feat, to be able to keep that ops tempo at such a high level. Aircraft were talking to each other, coming and going from their targets. That's a unique concept of warfare that this nation or the world has never seen, where you have warriors taking off, going into combat, and returning home after a 30-hour mission, walking home into the house and honey, what'd you do today?
The 30-hour missions were exhausting, but the B-2 crew tried to find a way to stay occupied during the long flight.
15 hours on the way out are broken up by a couple of every fuelings every 4 hours or so. And then you do your bombing, and then you come back home, same thing. So what we try to do is maximize the amount of downtime to relax, to study our targets, anything we can to keep our bodies as fresh as we can during the sortie.
Despite the successes in Kosovo, the B-2's substantial cost had remained a focal point of controversy. Originally planned as a fleet of 132 stealth bombers, the program was scaled down significantly, resulting in a total force of only 21 B-2s. Nevertheless, the B-2 is a vital part of a trio of long-range multi-purpose bombers that also includes the B-1 and the venerable B-52.
We've got some weapons upgrades coming along the line. We've just been certified with the Joint Standoff Weapon, starting into the cruise missile concept. So the B-2 can actually, if it has to, fight its way into a target area by launching cruise missiles and then delivering the JDAM, Joint Direct Attack Munition, which is extremely accurate.
With the B-2, you can go out, you can fly long distances, you can destroy targets within tens and sometimes ones of feet with precision weapons through any kind of weather that's out there. So if no one else can fly that night because the target area is socked in, here comes the mighty B-2 with its precision-guided weapons that doesn't need any assistance, comes in, delivers its weapons, and goes back home. That's why you need the B-2.
With our stealth capability, it allows us to be first in and create holes in the defensive environment that the conventional airplanes can now use to strike effectively. The B-2 is capable of getting in there first strike and basically putting the lights out.
The B-2 is definitely a long-term aircraft. The design is proven. The concept behind the design will last for a very long time. And its airframe, again, is just a very simple design that is so effective.
The B-2, proven in combat with its advanced stealth technology and versatility as both a nuclear deterrent and a multi-purpose bomber, is likely to remain a key element of the U.S. global military strategy for decades to come.
When you see the B-2 fly over and give you that profile of the flying wing, it is a stylish aircraft. It just shows efficiency mixed with style. I think the legacy of Northrop is to point the way to the future so that engineers today and in the future can look at what this man did and can move forward and take the United States into new technological realms of aviation.
However, despite the extraordinary success of the B-2, Jack Northrop's dream of fulfilling the skies with graceful flying wings has not yet been fully realized. Various challenges, including the expense and complexity of the computerized control systems needed for the flight stability, continue to impede the broader commercial acceptance of the flying wing concept. Nevertheless, as futuristic wing-like designs are once again being developed around the world, there is still a possibility that Jack Northrop's version of the flying wing, or something very much like it, could still represent the shape of things to come in aviation.
This is the Flying Wing, the product of years of engineering research by Northrop Aircraft and the United States Air Force. Today, it is the latest answer to aviation's demand for more speed, more range, and greater efficiency of operations. The Flying Wing can carry a larger load faster, farther, and with greater economy than conventional airplanes of similar size and power. Since the Wright brothers' airplane first flew at Kitty Hawk in 1903, Americans of this century have seen great advances in air transportation. Few men indeed can see the flying wing in operation without saying, "The plane of tomorrow is flying today." Since man first learned that mechanical wings could carry him into the sky, airmen have dreamed of the ideal airplane, one of maximum efficiency, in which every exposed surface would have the greatest possible useful purpose, contributing to the lift of the flying machine. 24 years of research and millions of hours of work are behind the production of these new aerial giants. The designers, the engineers, and many other men working with Northrop aircraft have long had this dream and have turned it into a reality, the flying wing.
This aeroplane was developed as an effective way to solve the old problem of reducing drag. Drag's rather hard to describe. A simple definition is to say that it's the resistance of the air to an aeroplane's forward passage. You've felt drag by putting your hand out of a car window, and probably you've noticed that you can reduce it by turning your hand edgewise, presenting less surface to the wind. In the flying wing, we've reduced drag by designing an airplane with a more efficient form. Its shape creates less resistance to forward motion and passes through the air more easily. Here, I'll illustrate it for you. Primitive man used a sled to transport loads greater than he could carry. This sled rubbed on the ground, just as aeroplanes rub against the air. It took sheer power to overcome the friction or drag of this conveyance. The larger the sled, the more drag surface it presented, and consequently the more power was required to overcome this drag. The logical solution lay in reducing drag to a minimum. So man developed the wheel, which permitted transportation of equal loads with greatly reduced power, or increased the loads and speed with the same amount of power. Since the beginning, aviation design has been confronted with much the same problem as was primitive man. Today's basic aircraft design still has unnecessarily large drag forces. The engines, cowlings, and the nacelles, the tail surfaces used for stability and control, the bulky extended fuselage. They all are causes of drag to be overcome at the expense of speed, operational range, payload, and power. In the flying wing, we have reduced drag by removing the external engines, cowlings, and the nacelles, the tail surfaces, and finally the fuselage itself. Now we sweep back the wings for purposes of balance, control, and stability. And we see a picture of the basic flying wing. And that briefly is what has been done about the problem of drag. Rather than try to overpower it, we've reduced it, knowing that when we eliminate the cause, we eliminate the effect. We now have an airplane which, due to its increased efficiency, is capable of transporting a given load 25% farther or faster than is possible with an ordinary airplane using the same power. That is what is meant by efficiency of design. Our second objective was greater efficiency of structure. In order to illustrate efficiency of structure, we can use these charts for comparison. Here is a massive bridge structure. Massive because of the engineering principles involved. Notice that all loads are transferred to central, concentrated points. This requires a ponderous, expensive structure to sustain the loads and resist the applied stresses, stresses that are multiplied in turn by the leverages of the spans. Now here on the same highway, carrying the same traffic load, is an economical causeway type of bridge. It does the same job as the first bridge, with a much simpler structure and a fraction of the material. The answer is simple. Stresses are absorbed and weights are sustained by the individual units or pilings. And in the same way, this comparison may be applied to conventional and all-wing aircraft. In the ordinary type, the lift which carries the load works on the wing from tip to tip, but the bulk of the weight is centrally located, necessitating heavier wing construction, particularly at the roots or points of suspension. In the flying wing, the same weights, distributed over the span of the wing, are sustained by individual areas or lift forces, permitting a large saving in structural weight at no sacrifice of strength. This saving is convertible to additional payload or fuel. And that, very simply, is what is meant by efficiency of structure.
Today, Northrop men know well that by combining efficiency of design and efficiency of structure, the result is a high-lift, low-drag flying wing, which can carry a greater load, carry it farther, carry it higher, and carry it faster than conventional airplanes of similar size and power. At far-flung bases and remote corners of the globe, large hangars to house big airplanes are usually hard to find. When these planes are repaired and maintained, the men must work in the open, often in bitter weather, which slows them down and makes the task far more difficult and costly in time and money. But not the flying wing. To shelter the wing requires only a small and modest structure, hardly more than a large Quonset. Placed on dollies, the wing can be trundled sideways into its hangar, a hangar that is small, economical, and easily constructed. As easy to maintain as it is to house, the flying wing is built low to the ground and can be easily serviced. Short ladders or low platforms available at any airport are all that are required to reach almost any part of even a large flying wing. Where outdoor storage is necessary, especially during cold weather, this is a great aid when all surfaces must be cleared of ice or snow prior to takeoff. With these additional advantages, it is little wonder that forward-thinking aviation experts already are envisioning the day when giant flying wing transports will enable world air travelers to fly faster and farther at reduced fares in a degree of comfort surpassing the most modern ocean liner.
Tailless folly, I call it.
Well, sounds as if someone has an opinion on the flying wing.
Now I ask you, who ever heard of airplanes without tails? Birds have tails, haven't they? If they didn't need them, they wouldn't have them. Flying wings. Huh.
Now there's a real expert, an authority on any subject. His ancestors were all authorities, too. For instance?
Steamboats. It's ridiculous. Who ever heard of a boat without sails? Fulton's folly, I called it. Steam trains. It's ridiculous. Who ever heard of cars without horses? 18 miles an hour, they say. They're flying machines. It's ridiculous. Who ever heard of a man flying? Never be practical. Who ever heard of an airplane without a tail? No stability, I tell you. Won't be able to fly. They'll never get that thing off the ground. They should have asked me. I studied a little bit about airplanes.
Recognize him? He's one of that group of skeptics who just can't understand any scientific advancement and won't believe it when he sees it. An open mind and a little inquiry would disclose the fact that the engineers haven't changed the basic principles of stability at all in building the wing. They've merely arranged the control surfaces in a different manner, in a form our skeptic doesn't recognize, thereby reducing drag by eliminating the tail surfaces and the fuselage that supports them. Yes, it's just about that simple and logical. Remember as a youngster when you seesawed on a plank? Sometimes there was a heavier boy on the other end, and you had to move out further to establish a balance. With both of you at the ends, your little brother had quite a time moving the plank. But once in balance, you could both move in and out proportionately to maintain that balance. And when you were close to the pivot, little brother could swing you lots easier than when you were out at the end. Now the airplane is balanced about its center of gravity in the same way as the seesaw was on its pivot. And when all of its weight is concentrated close to the center of gravity, as it is in the flying wing, The size of the tail can be reduced or moved much closer to the wing, and the same degree of stability and control will be retained. Here is the top view of an ordinary airplane, and this is what the skeptic failed to investigate. If the load usually spread out the length of the fuselage is carried in the wing close to the center of gravity, then the fuselage can be removed and the tail moved up close to the wing. Now, the tail has much less work to do and therefore requires a shorter moment arm. Swept back or V-shaped wings are coming into general use even on conventional planes because of their recognized advantages in the reduction of drag at high speed. Thus, the wing is simply swept back, and one half the tail is combined with each wingtip. All the original elements needed for stability remain completely effective, but over half the drag of the original airplane has been eliminated. Having already discussed efficiency of design, structure, and maintenance, there's but one final point: operation. Extremely important in any aircraft is efficiency of operation. The handling characteristics of the wing are important to the pilot.
That's right. Makes a lot of difference if a man who flies a plane likes the way it operates. Because of its stability, ease of handling, and maneuverability, the wing is as simple to fly as a conventional type airplane. Despite its 100-ton gross weight, it still responds to fingertip control pressures. But let's get aboard and I'll show you the inside story. First, the controls. The flight controls in the cockpit operate in a normal fashion and differ very little from those in a conventional plane. Foot pedals operate the rudders, which consist of double split flaps, similar to dive flaps, located at the wingtips. When a rudder pedal is depressed, the flaps open to produce drag at the required wingtip. Here's an easy way to explain the action of wingtip rudders. Notice that when drag or pressure is applied to a wingtip, the plane pivots around its central axis, exactly as if rudder were applied. Consequently, our wingtip rudders give us the same control as the rudder on a standard type plane. On the flying wing, both pedals may be operated at the same time. This creates an air brake effect, increasing the rate of descent or reducing the airspeed, a valuable asset in landing a clean modern airplane of this type. This air brake feature is the only variation from a conventional control arrangement. Longitudinal and lateral control are maintained by elevons, a combination of the standard elevators and ailerons. When the control column is pulled back, the elevons, located just inboard of the rudders, are moved upward, causing the wing to climb. Forward movement of the control column moves the elevons downward, resulting in an opposite or diving effect. These operations of the control column and the elevons produce the same effect as the elevators on a conventional type airplane. Lateral rolling effect is achieved by operating the control wheel in the normal fashion. This works the elevons in the same way that ailerons are operated on a standard ship. For example, turning the wheel to the left raises the left elevon and depresses the right, causing the airplane to roll to the left. By turning the wheel to the right, the plane will roll to the right. The plane can either climb and turn or dive and turn by using longitudinal and lateral control at the same time. Okay, Frank, let's start the engines.
Hello, Tower. This is Air Force 2367. Taxi clearance, please.
With its 8 jet engines, the Wing is one of the most powerful planes in the air. Ground handling and taxiing are identical to that of any other large airplane having a steerable nose wheel. This ease of handling simplifies parking and storage operations. Notice that the pilot of the Flying Wing has excellent forward, downward, and round-the-clock vision, which minimizes taxiing hazards.
Hello, Tower. This is Air Force 2367. Ready for takeoff. Over.
Air Force 2367, this is the Tower. Clear for takeoff.
2367. Roger.
This 100-ton giant is airborne. Notice its phenomenal rate of climb. Ease of operation, together with low noise and vibration levels, make long-distance operation almost a pleasure. Because of the pressurized cabin and temperature control, grueling hours of long-range flying can be accomplished with a minimum of pilot fatigue, even at altitudes above 40,000 feet. As pilots know, the Flying Wing is an easy plane to handle. When a rudder pedal is depressed, drag is induced by the opening of the split rudders, and the plane is pulled in that direction. Rudders are depressed, an air brake effect is created for short approaches or steep descents over landing hazards. Normal control column movement results in a climb, a dive, or bank as desired. Controls operated by dual hydraulic systems, plus an electrical standby, the Flying Wing is the most maneuverable large aeroplane in the sky. Powerful weapon, a plane that can hold its own against enemy fighters. The wing has a small frontal area and profile, making it difficult to hit or to detect with radar. With its relatively low wing loading and high speed, the wing is capable of defensive or offensive maneuvers that would stall out most fighters, particularly at high altitudes, where the rarefied air places limitations on airplanes with high wing loading. Imagine you're an attacking pilot. Not much to hit in this slim, clean line, is there? especially if it's going away at more than 500 miles an hour. Should one or more engines be knocked out, the wing is still a formidable fighting machine. It can be effectively maneuvered by making a slight adjustment in trim. Even with all the engines on one side inoperative, it has good performance, flies easily and efficiently. As a bomber, a long-range high-payload cargo carrier, or a giant passenger transport, the sleek, knife-edge flying wing has as its keynote efficiency. Efficiency of design, efficiency of structure, efficiency of maintenance, and operation. It is the most useful and efficient airplane the world has yet seen.
The A-12 would have been a maintenance nightmare. They needed something more stealthy than the planes that they had on the carrier decks for the Navy. And so, in my view, they overreached by getting a overly sophisticated stealth version, and it was going to be a flying wing design. And the flying wing had a bad history in the B-2 bomber.
The A-12 program was substantially overcost and behind in schedule. Given the fact that this information was available in all three offices, why was it ignored?
I don't know.
Well, who would normally get that kind of information?
The program office would get it, and
would it normally come to your attention? Or Admiral
No, sir.
Morris, would it come to your attention?
No, sir.
You never get that kind of information?
No, sir.
Well, you fellows better get something so the right hand and the left hand knows what's going on.
Back before the A-12, the Navy had the A-6E Intruder, which it was using in Vietnam, and it was just getting old, and they decided to replace the airplane. And when they thought about replacing it, the first thought they had was, how do we get through the very dense Soviet radar network? And since the Air Force was working on stealth, the Navy, in somewhat of a competitive mode, decided to have the same thing so that they could also say that they could breach the Soviet radar system. In the beginning of thinking about stealth for the Navy, they came up with some modifications to the A-6 to make it stealthy. And they were so excited about it, they had various companies doing things, one of which was Grumman, and they invited Secretary Lycoming to come up and take a look at it. Lycoming was ready to take the A-6E, make it an A-6F, which had basically F-15E avionics, which would do the job for the time being, because he felt that was adequate to get through the Russian radar system. He didn't want to get into stealth until it was proven by all of the other programs that were underway at the time, which were the F-117, the B-2, and the Navy's version of the F-22. And until and if stealth was a proven commodity, then and only then did he want to dump Navy money into it. And Lycoming's comment to me was that it looked like putting fins on a dump truck, and there was no way it was going to make it stealthy, that the Navy would indeed have to go back to the drawing board and start from scratch.
I was on the aircraft carrier John F. Kennedy for 7.5 months, and I flew in every plane on the deck, and the A-6 had an extra seat most of the time because they were used for refueling. KA-6B was the designation. The carrier is designed a certain way to accommodate rectangular airplanes on its flight deck. And for instance, the A-6 you'll see on a carrier, the A-6 has its tail out over the water. Well, a flying wing, you can't do that. And so they kind of fouled up the air boss, who kept trying to figure out how to park this if they ever did get it to fly. And as you know, it didn't fly, and it was just a model, and it never was flight tested. In my view, they were over-ambitious with the design, they were over-ambitious with the technical details, and they had more expectations from the stealth than proved realistic. And the big problem with the Navy plane when you land at 80 miles an hour on a carrier deck at full power, because if you miss one of the 4 wires stretched across the deck, you have to be ready to take off again and try landing one more time on the Navy aircraft carrier. So it takes a very strong airplane, and they used to call the F-14 a product of Grumman Iron Works because it was so rugged it could handle the stress of being in a crash landing, basically.
Well, over the years, the Navy has used the fact that an airplane has to be navalized in order to fly off of a carrier, predominantly because it has to be able to catch a tailhook when it lands, and it needs extra structure and some other things as far as clearance and many other modifications that the Navy deems necessary. However, whenever the Navy wants a plane, it'll waive as many of those as it wants. And when it doesn't want a plane, it uses the fact that it's not navalized as the reason. And so the Navy said, no, we need our own airplanes, which is what happened in the F-16s. They navalized the YF-17 and it became renamed as the F-18.
The idea of putting an A-12 on an aircraft carrier ignores the realities of what it's like to have maintenance of airplanes on an aircraft carrier. The seawater gets into cracks on the plane. The sailors are forever sanding and patching up the skins of existing airplanes. And the stealth, if the B-2 is any example where they can't leave it out in the rain, for instance, the stealth flying wing of an A-12 would just be a nightmare, be a headache for the maintenance people. And most people don't know this, but sailors are okay, they're great. They work their tails off out on aircraft carriers, but they're not technically astute enough to maintain the testing equipment needed for an aircraft carrier, the planes it has. It has about 80 planes. So what do? They bring technicians along, civilian technicians, they call them tech reps. And the good question would be, how could we go to war, for instance, if the civilian tech rep says, I'm not going? You couldn't tune up the airplanes, you couldn't tune up the engines.
I had a major general who was retired tell me that if you think the Pentagon is a place for making war plans, you're mistaken. That the real purpose of the Pentagon is to fight for budget share. So the whole thing is this big dance. Do we get our percentage that we typically get? So when the Navy saw the Air Force starting to get all these stealth airplanes, of course it became very jealous because it could see that its role was going to diminish. So it wanted to come up with a stealth airplane. And that's exactly why they wanted to put stealth on the A-6. The Navy issued a contract to two competitors, General Dynamics teaming with McDonnell Douglas, and then Northrop. They said it will be for a $4.8 billion with a B dollar fixed price contract to build some 10 or 12, I can't remember the actual number, of airplanes in a research and development contract. They said, these are the prices, this is what it's going to cost, this is what we're willing to pay for it, etc. At no time did Northrop ever agree to build it for that price. So if you know anything about contract law, if you're not going to adhere to the specifications of the contract, you're really not a competitor. And to keep the charade going that there really was a competition, the Navy kept Northrop in the competition so that McDonnell Douglas and GD would think there was a real competition, which of course is a violation of a lot of things. So there was a charade from the beginning. But in January of 1988, the Navy issued a fixed price contract to the team of McDonnell Douglas and General Dynamics. So there was a charade from the beginning. General Dynamics did all the design work. McDonnell Douglas was in it just for the navalized aspects of it. Not to say they didn't know anything about stealth, but GD was way down the line in terms of development. The contract began in January, and in March of '89, a year or so later, Dick Cheney came in the Pentagon as the Secretary of Defense. When the A-12 was being designed, the Air Force did some simulation, and they nicknamed it Bright Star because they said it was so unstealthy. In fact, former Undersecretary of Defense Kaminsky said in one of his depositions that one of the objections to the trailing edge of the airplane was that when you irradiated a shape like that, which was the Dorito, the triangular shape, you get a bloom coming back over the top of the airplane, which lights up the radar. So he said it was really not the proper design, and that's why on the B-2 and on the competitor from Northrop to the A-12, internally called by some A-11, it had a jagged edge, a sort of a sawtooth trailing edge, so that the thing wouldn't have the problems that Kaminsky mentioned. One of the events that happened during 1984 was a German pilot flew a Cessna 182 into Red Square. He flew it all the way from Helsinki down to Moscow. And for a lot of people, that was evidence that the Russian radar network was porous. It didn't stick because there's too much money involved. When you have a lot of money involved, contractors say, well, that was just a fluke, and if we were going to have a bunch of airplanes, they'd light up all the radar sites. So they use whatever excuse they can to justify keeping the money flow.
The A-12, they wanted it to make it out of magical materials, boron and fibers and so forth. And that is fine, it's lighter, but they found out that they had to make it so thick that to get the strength they needed, the cost kept climbing up and up.
I don't think there's any question that the concept of stealth is valid from at least one position. And you can optimize any object to provide less of a radar return. But the problem is that it's only good from that one position, and everything off of that, say in this case, a nose-on position, is a compromise. There's two ways that an airplane is made stealthy. One is by the material that's covering it, which is called radar-absorbent material, or RAM. And the other is the shape of the airplane. Back in the beginning, when Northrop was competing against the F-117, Lockheed was using flat plates, kind of like one of those mirrored balls you see in a ballroom when the light hits it and it bounces all over the place. You don't get a direct return. And Northrop was trying to solve the problem by smoothing and rounding the edges. And in fact, I demonstrated that to myself one time. When I was doing research on the book, I went down and interviewed John Cashin, who was the stealth designer of the B-2, and spent several days with him in Australia. And when I came back, I had a laser gun, which I was using in a Radio Shack, and I was putting the laser all over the store, and I once hit some very curvaceous coverings for what was obviously a boombox speaker setup in the back of a truck. And while the laser was giving me a return wherever I went all over the store, regardless of color or anything else, when I hit this boombox, which had very compound curves on it, the spot completely disappeared. And so I called up Cashin in Australia and I said, hey, I just had an interesting experience today. And he said, you just broke the code. Problem is, you can't break the code from all positions. So if you want to make the bottom of the airplane stealthy, then something's going to give on the top and vice versa. So it depends on you're coming in low or you're coming in high. So stealth is always a compromise. If you want to think about how radar absorbing material works, think of a flashlight, but that only has one color. So the flashlight, let's say it's red, and let's say your airplane is white. Well, if you put a red flashlight on a white airplane, you're going to see it. But what if the airplane is covered with, let's say, velvet that's red, same color as the flashlight? You put the flashlight on it, it's gone. You don't see, there's no reflection. So those two things combined can make an airplane less able to be seen. The F-117 came before anybody else. It actually made its first flight before the A-12 program began. So it came first, then the F-117 prototypes came along while the A-12 was in its formative years. But the F-117 was the first manned stealth aircraft for the U.S. The F-117 in Serbia had a higher loss rate than the F-16, flying in equally dangerous areas. the F-117, one of them got shot down, which made all the news. What didn't make the news was one of them was shot up so badly it flew back, limped back home, never to fly again during the war. So even with one shot down, it would have a higher loss rate than the F-16 because the F-16s flew a lot more sorties. So a friend of mine went over and interviewed a general after this first shoot down happened. And when he interviewed the general, he brought up the second one, and the general said, "I don't want to talk about it." So there's no question in my mind that it happened. I've had it confirmed many different ways.
Stealth is a concept that's better in the laboratory than it is in actuality. Now, what are you going to do to drop a bomb on Russia? You've got a stealth shape, so you're going to open the bomb doors, right? And that's going to give away your position to any basic radar. So I always thought the stealth feature was too expensive for what you got in return. And it's not really invisible. That's a myth. A stealth airplane can be seen on radar if it's close enough. But the F-117, for instance, was the hero in a sense of the first Gulf War. But you could see that. And it's good for very precise targets, and but it's not a Chevrolet or a Ford. It's a handcrafted airplane, and the maintenance is a devil, and it's not invisible anyhow, but it is less visible than the conventional airplane.
Based on an article a friend of mine and I wrote, we were invited to come up to Nellis because the Air Force wanted to show us how great the F-22 was, that we were somehow had been misled and didn't appreciate how stealthy it was. And in one of the, actually it was the first or second series that we watched, an F-5 bagged an F-22. Well, of course, I interrogated, you might call it interrogation, the commanding officer of the squadron that evening, and he said, "Oh, it was just a fluke." But the point was that there was a $360 million airplane against a $20 million airplane. And the point is, it shouldn't happen. Shouldn't happen at all, not being a fluke. He said the pilot was inexperienced. There's always an excuse when it doesn't work. But when they sell it, it works, perfectly. The Navy wanted to have a stealth airplane so that when it invaded Russia as part of the war plan, it could make it all the way in and out without being shot down by the Russian radar sites. The Russian radar sites were placed every so often, and the idea was that if you had a stealthy airplane, then the radar would only be able to broadcast circles like this, and you could fly through these big gaps, whereas if you were a conventional airplane, the gaps would overlap and you could never get through. Now, Secretary Lycoming disagreed with that because he said he had flown in A-6s up in the desert where we had captured Soviet radars, and he said we demonstrated, or the Navy demonstrated to his satisfaction, that we could penetrate the Russian radar. Furthermore, the Russians had all these airplanes rusting all over the place, and ships, so it was clear the Russians couldn't afford to build up more densely populated radar sites, so he thought it was not necessary.
The Navy did not have a new airplane, so to speak, so the A-12 was going to be all the bells and whistles that the Air Force was putting in the F-22. Problem is this, that the cost of the F-22 per airplane, counting research and development, is $350 million for one airplane. That means you're in a death spiral on procurement. You can't buy enough of them, no matter how high the Pentagon budget gets, and it's already about $1 trillion a year if you count what it costs for Homeland Defense and what it costs to build nuclear bombs. $1 trillion is more like it than $700 billion. Anyhow, point of story is that you can't have an airplane do everything, even though McNamara tried it with the F-111, which was the TFX. He wanted to be able to bomb, dogfight, have the Air Force buy it, the Navy buy it, the Marine Corps buy it. And specialized roles mean specialized airplanes. And the idea of asking one airplane to do everything just is never proven out. It's not practical. And as I say, if you get an airplane so costly, like the F-22 is $350 million, one airplane, how many of them are you going to be able to buy? And so there is a strength in quantity as well as in quality. And the Navy pilots were kind of begrudgingly accepting the F-18E and F, but they really would have liked a new fancy airplane like the A-12. But that's a pilot. You wouldn't expect a pilot not to want the latest weapon that he could get to fly. I mean, we're all that way in America. we want the latest gadgetry. But from a standpoint of strategy and quantity and ease of maintenance and cost, I just think the F-22 is a loser, and I think the A-12 would have been a loser. Well, when our photographer went out to take a picture of it, a good part of it was just pasted together material. There was not a flyable plane. So I would say they never got more than halfway towards getting a real airplane, and it was a comical show of this is what it will look like, but it's like an airplane made out of soap, or or a car when they start out. They carve it first out of a cake of soap. So it didn't get very far, and it certainly was not flight tested at all. Zero. Never took off, never landed. And they just couldn't get it strong enough to withstand the landing on a Navy carrier deck.
When you have a black program, there are very few people that know what's really going on. In fact, one of the fellows I interviewed was a staff member on the Research and Development Subcommittee, and he said it always amazed him that he knew all about the A-12 program and that 95% of the people on the committee had no clue. The A-12 was designed to carry two missiles internally called TSAM, spelled T-S-S-A-M, but it was so secret that the designers of the A-12 were not allowed to see anything about the TSAM. It was completely compartmentalized. They just were allowed to keep a space for those missiles to be carried in.
Well, the contractors do have a point in saying that they were so compartmentalized by the secrecy impositions on them that one guy in one plant couldn't talk to another guy in another plant even if they were working on the same problem because of the secrecy restrictions. So they do have a point in saying that it was overclassified, and scientists and engineers, they love to cross-fertilize, and that's the way you get things done. But if you've got a secrecy wall separating you from a guy who knows the answer, that's a legitimate point. And there was a lot of secrecy imposed on the A-12. There could have been a certain restriction on the stealth exchange of information that I know about. It was overly classified, and you couldn't move to one office to another and talk to a guy without certain permission.
The contract began in January, and in March of '89, a year or so later, Dick Cheney came in the Pentagon as the Secretary of Defense.
Well, Cheney in those days, before he got kind of over the top about a number of issues when he was Vice President of the United States, but when he was Secretary of Defense, and I covered him at that time, I thought he had a sane approach to things. He was a former White House operative who was deputy to Donald Rumsfeld and lobbying Congress. He knew the realities of Congress, but he was a layman. He was not an engineer, never was a pilot. The A-12 had, as every airplane when it's ordered from the Pentagon, has a set of specifications, has a set of performance goals, set of performance requirements, has to have a certain speed, has to be a certain weight, has to be able to do certain things, has to be able to go so fast. And it was obvious in the design phase and in the research and development phase that the A-12 was not going to be able to live up to the promised specs. These promised specs are called brochuremanship, and you're trying to sell the airplane to the Pentagon, and you're saying it can do everything but make cookies. And you put a film together and you say this will be a wondrous machine, but when it comes to flying it, they came into all kinds of problems.
The Navy saw the Air Force starting to get all these stealth airplanes, Of course, it became very jealous because it could see that its role was going to diminish. So it wanted to come up with a stealth airplane.
In my view, they were over-ambitious with the design, they were over-ambitious with the technical details, and they had more expectations from the stealth than proved realistic.
General Dynamics, teaming with McDonnell Douglas and then Northrop, they said that it will be for a $4.8 billion with a B dollar fixed price contract. At no time did Northrop ever agree to build it for that price. If you're not going to adhere to the specifications of the contract, you're really not a competitor. The Navy kept Northrop in the competition so that McDonnell Douglas and GD would think there was a real competition, which of course is a violation of a lot of things. So there was a charade from the beginning. By the fall of 1989, the A-12 was exhibiting weight, schedule, and cost problems. So in the fall of '89, after the Berlin Wall fell, Dick Cheney issued a memorandum asking for people to contribute information to what he called the Major Aircraft Review. He wanted to go up and talk to Congress, since he was a former congressman himself, in April of 1990 and say, here's the state of the contract. Dick Cheney issued a memorandum asking for people to contribute to a presentation he wanted to make the following April 1990, April 26th to be exact. And he asked for these contributors, and it took several months, and people would contribute information. And about a month before he made his presentation, he got 4 warnings in writing and verbally that the A-12 was a problem. One of them was a briefing, oral briefing, said it was $1 billion over budget. And since it was a fixed price program, it meant that GD and Mac Air would have to pay for that. Cheney has no recollection of that meeting. And according to his Undersecretary of Defense, when I told him that Cheney said he had no recollection, he said, well, that's impossible.
Well, I think that the merchants of death out there oversold the A-12, and they said they could deliver on this product, which was very fanciful, and didn't happen.
Because that Undersecretary of Defense, John Betty, had written Cheney a memorandum, which also sent to everybody in the upper echelons of the Department of Defense, saying that all the airplane programs that you're going to be briefing on April 26th, the A-12 is the only one I have a problem with. And it was his people that briefed Cheney on it being $1 billion over budget. Whenever there's large amounts of money involved, the Department of Defense has various levels of decision-making, and in one of these final decision-making, they all agreed they were going to have a new airplane. The title of my book is called The $5 Billion Misunderstanding. And the reason it's called a misunderstanding is because half the room left thinking it was going to be a new airplane, which was code for stealth, and the other half thought it was going to be an upgraded airplane like the A6F. Dick Cheney had lots of warnings about the A-12 being a problem. And then when he testified in front of Congress on April 26, he said the A-12 has been well handled to this point.
I think the reason that the A-12 was pushed was not so they'd have something that would be a miniature B-2 stealth bomber, for instance. It was more the contractors promising more than they could deliver. And the costs also went skyrocketing.
When Cheney decided to terminate the A-12, he called in the Navy and gave them a sort of last chance to tell him why he shouldn't terminate it. They made their arguments, and Cheney decided to terminate the contract. There was an A-12 program, but the only thing that was in the A-12 program was this contract. So in a sense, you don't terminate a program for default. You can only terminate a contract for default. He didn't say, I'm terminating the contract for default. He said, I'm terminating the A-12. And he later acknowledged it was for the contract. He then turned the responsibility over to the Navy's contracting officer, and that officer had a choice between termination for default or termination for the convenience of the government. In one case, the contractor would be paid, and so would the subs, and in the other case, they get nothing. He being the contracting officer, felt that to let the contractors be paid would be a windfall and was not in the best interest of the government. He wanted to continue the program because he knew how desperately the Navy wanted it. There are several investigations about the A-12 program that happened over the summer of 1990. In July of 1990, Cheney issued a letter to the Senate Majority Leader asking for more money for the A-12. He was denied the money. And from that point on, Cheney and his group of leaders did everything they could to justify the cancellation of the A-12. Remember, they had a war coming up in January of 91, which was against Iraq. So they were looking for money anywhere they could find it. So Cheney canceled the contract, and the Navy implemented the cancellation. The contract, if he hadn't canceled it, they would have been obligated to issue $553 million, roughly $500 million, against the contract, and they wanted to avoid that because they wanted to use it for other purposes. When Dick Cheney terminated the contract, which he did, which he said he did, he stepped into the shoes of the Navy's contracting officer. That meant he had to follow certain regulations. The regulations require a 7-step process, and that 7-step process takes several months to do. Because this was done over the weekend and the following Monday, $553 million was due to be applied to the contract. It was a rush, and it was all done on that Monday. And what they did was, they meaning the contracting officer and his legal assistant, they took out an older document that was done to terminate for default the Lockheed P-7, which was a follow-on concept to the Orion P-3, and they dusted it off and they filled in the blanks with typos, blanks, and inappropriate statements. For example, one of them was, they said that the A-12 was being terminated because it couldn't make its runway takeoff length. Well, you don't have a runway takeoff length requirement in an A-12 because it's shot off an aircraft carrier with a catapult. And when she was interviewed, this is Peg Olson, when she was interviewed in trial, the attorney asked her, well, now, Miss Olson, isn't it reasonable to say that with the slightest amount of review you would have caught these? And she said yes. And the attorney told me it was one of the most sophomoric pieces of work he'd ever seen. So that is what Cheney should have done but didn't do when he terminated the contract for default. He terminated it, well, it's not really fair to say he terminated it for default. He terminated the contract, and the Navy's contracting officer, acting as a pencil, terminated it for default. But that was just fulfilling Cheney's wishes, because if you didn't terminate it for default, you'd have to pay out all the money. And that's what they were trying to avoid, because the war was coming up in just a few weeks. Cheney made false statements to the Congress because he said that no one could tell him how much the airplane was going to cost, which is why he terminated the contract. When he made that statement, which was about 6 weeks after he had done it, I guess he had forgotten that he was told the day he canceled the contract a very precise number, $7.5 billion is what it would take to finish the program. That, by the way, was the exact number that the Navy used before the program began when it was trying to estimate what it would cost. So Cheney, on many occasions, made statements that were just not true. And again, to accuse somebody of, I'm not accusing him of lying, because that means I know what his mental state is. But I can tell you that the statements were false. For example, he wrote a memo to President Bush, the first one, and said, my team didn't tell me how bad the A-12 program was. Well, he got 4 memos on the A-12 program, verbally or in writing, so he knew exactly what it was. In fact, the guy who told Cheney did you say $1 billion overrun? And Cheney, and the guy answered yes. So Cheney was well briefed on this. So he just must have had some sort of disassociation with what he'd been told to be able to say no one could tell me what it was going to cost. Right after Cheney terminated the contract, of course, that was in January. In June, the contractors filed a lawsuit, June of 1991. Here we're coming up to 2011, that's 20 years. So why did it take so long? Well, the reason it took so long is because the contractors won at the trial level and the government kept appealing. Okay? And in those appeals, you have wins and losses. And in each case, there was either a neutral, send it back to the trial for more clarification, or the government won. So finally, the contractors are appealing to the U.S. Supreme Court on one of about 20 reasons. What happens in a contract when people sue each other? They start coming up with excuses. Well, you didn't do this or you didn't do that. So there were a bunch of reasons that the contractor cited as to why they were unable to fulfill the contract, most of which I felt were legitimate. So they get to the Supreme Court and they take out what they think is their best shot, and that was the State Secrets Act. Essentially, the State Secrets Act says this: in order for us, the government, to defend ourselves, we would have to divulge information that is so secret it would harm the country. And therefore, we are not going to proceed. Now, according to the legal advice I've been told, the government's perfectly at liberty to do that. But if they take that position, then they have to pay the contractors. But in this case, the government is arguing, not only do we not have to give you any information so that you can show that you were not at fault, you, the contractors, but we're not going to tell you anything. We're just not going to give you anything, and so you're going to lose. And there's some argument in the Supreme Court oral argument that, hey, that's not really fair. You know, if you're gonna do that, then you got to give up the money. You don't have to tell them, but you got to give up the money. You lose.
So the way the contractors get well, this is an old game. Everybody who's in Pentagon procurement knows it. They say, well, you changed 1,000 things on this airplane, and we're going to charge you for each one of those changes. That's how they get well. That's how they make money. The basic problem with military procurement in the United States today is that we're allowing the defense contractors, allied with the Congress, to take us to the poorhouse in Cadillacs. So what do the contractors do? That's a severe loss of money if it's canceled for good cause, because it couldn't live up to the specifications in the contract. So they said, in the first appeal to the courts, which I covered some of, that he didn't follow correct procedures, that he ignored the rules of canceling a contract. So the issue going into the first round, and there's been several rounds in the courts, as you know, and it's still not over, that the poles of the argument were Cheney was beyond his authority by the way he canceled the contract. And the Navy's response through the Secretary of Defense was it couldn't live up to the contract performance-wise, specifications-wise, so it's a flawed product and we're not going to buy it. So we have just cause for canceling the contract because it can't perform as advertised. The contractors' fallback, McDonnell Douglas and General Dynamics, was, yeah, but there's certain ways that you have to cancel a contract and there's certain appeal processes and you ignored all those rules. So that was the issue. Looking through Defense Secretary Cheney's end of the telescope, I can see why he couldn't get answers to A, no one knows what it's going to cost, B, no one knows what it will be able to do, C, nobody knows whether it can withstand the pressures of a carrier deck. And what was the threat? Who had a A-12? Nobody. And you could make a case nowadays, why not deal with it with unmanned aircraft and then send in something simpler and cheaper than the A-12. Cheney couldn't get solid answers, and he just said, "The hell with it, cancel it." And he went out to St. Louis and canceled it on the spot.
The history of the Department of Defense is that all programs run into problems, and there was nothing unique about the A-12. There was no reason to think that it wouldn't continue. I mean, historically, programs get into problems, they throw money at it, and it either gets fixed or it doesn't get fixed, but in most cases, it continues whether it's fixed or not. The A-12 program was doomed to failure from the very beginning for the simple reason that not enough money was funded for the airplane, for the development of the airplane. The 4.8 was less than the 6.8 that was appropriated for just one phase of the F-22. Basically, all airplanes in development go through 3 phases. At the time, the first phase was called concept formulation, where you have a bunch of paper studies. The second phase was demonstration and validation portion of the advanced tactical fighter, which eventually became the F-22. Both Northrop and Lockheed developed airplanes. They each contributed 2 airplanes. One was called the YF-23, that was the Northrop airplane. One was called the YF-22, that was the Lockheed airplane. The combined amount of money spent on that phase of the airplane was a significant amount more than was programmed for the entire A-12 program. So you have these 3 phases: concept formulation, demonstration and validation, and then full-scale development. That's when you build the actual airplanes and start flying what's supposed to be the end product. There was never enough money in the A-12 program. It was doomed because there wasn't enough money, and everybody knew it. Everybody I ever interviewed said everybody knew it was doomed, but like all programs, they thought they were going to get whole on production. So when Dick Cheney, when he gave his talk on April 26, 1990, the Major Aircraft Review, he basically cut the program in half. So there was no way they were going to get whole. So the contractors came and talked to Dick Cheney in June and said, "We can't get there from here. There's not enough money." And Cheney had some options, but he doesn't even remember that conversation either. So it wasn't until July that he asked for more money. Congress didn't give it to him, so the A-12 program never had enough money to adequately do what needed to be done. When you're talking about research and development, you don't really know what you don't know. You don't really know when things are going to happen. So if you came to me and said, how much would I charge to do something I had never done before, I'd say, I don't know, I'll just bill you hourly until I get there. A friend of mine once said, inspirations come, but not on schedule. So that's what Tom Jones told me when I interviewed him about his part of the A-12 competition. He said, we built stealth airplanes. We knew what the problems were. We knew that you could never make a fixed price contract for a research and development airplane because you don't know. So he thought it was just ludicrous. So that's why he made his so expensive that they were never really considered a competitor, because he didn't want to end up losing money. So he essentially converted his proposal from fixed price to a cost plus. And that's why the A-12 was never going to be built, because it didn't have enough money in the first place. If you look at the F-22 program, you had the middle phase, the demonstration and validation. That was probably 20 or 30% more than the whole A-12 program. And since then, they spent probably in today's dollars, 15 or 20 billion dollars. The A-12 program was premised on the fact that the Air Force was going to share information with the Navy. That was done in 2 ways. One, it was in the specification, which was incorporated into the contract, that the Air Force would give the information. And secondly, there was a memorandum of understanding between the Secretary of the Air Force and the Secretary of the Navy that they would share information. That information was never shared. It was asked for many times. It was never forthcoming. So that meant that the contractors who had never been cleared into any stealth programs were not able to use, if they had some personal knowledge about stealth, they were not able to use it because they had to justify the basis on which they were building the airplane. So it would be kind of like a blind man trying to tell you what the inside of a cave looked like, and you can't touch the walls. There's just no way to figure out how to do it. So they ran down a bunch of blind alleys, but towards the end, they actually started getting closer and closer. There is a duty, according to many of the lawyers that I've talked to on the program, a famous case called Helene Curtis, that says that a government can not remain silent and allow a contractor to enter into a ruinous course when the government has the information. They have a duty to share it. And when the judge in the first trial looked at the contract, he said, you have a duty to share it based on the specification. Never happened.
Well, just to back up on the realities of contracting, when Robert S. McNamara came to office at the Pentagon as Secretary of Defense in 1961, there was a competition for what was then called the Tactical Fighter Experimental, TFX, which became the F-111. And they had 3 separate competitions for the first time. McNamara had demanded that the competing contractors, who were then Boeing and General Dynamics, share each other's information after every competition of those 3 different awards, the 3 different competitions. And so it's standard practice that once you're bidding for a government contract and you have some technical information that would help your competitor, the Pentagon has the right under most contracts to tell X what Y knows that he doesn't know. And so it would be unusual for a contract where taxpayers' money is being spent for the F-1117 people not be able to talk to the A-12 people. But it could have been. I don't know that for a fact. But the standard practice is you share information because it's all owned by the government.
The reason that the Air Force did not share the information, in my opinion and the opinion of many other people, is that we're back to the budget share problem. The Air Force, missions and budget share. The Air Force wants to have it all. The Navy wants to have it all. Anybody who doubts this, all they have to do is go back and look at the carrier battles back in right after World War II. The Air Force said, you don't need to give money to the Navy because with our B-36 that's coming online, we can drop nuclear bombs all over the world at a moment's notice, so the Navy is irrelevant. The Navy, on the other hand, argued, well, you may not always want to eviscerate your enemy. You may just want to kick him in the toe, and that's when you need the aircraft carrier. So there's always been this rivalry and jealousy between the services, and they guard, like you can't believe, their budgets, and they will not do anything to cooperate with each other. Northrop didn't share their technology with the A-12 team because, after all, it'd be like a competitor sharing with another competitor. They were competitors. So the Air Force didn't want to do it based on just parochial interests, and Northrop wasn't going to share because they're a competitor in the program.
First of all, what happens in the real world is contractors have to make a living, right? So they're always trying to sell the better mousetrap. And they're continually promising things they cannot deliver on. They can't deliver on cost, they can't deliver on performance. And the reformers that I respect say, why not have a fly before buy? Why not compete 2 airplanes against each other and see which one is better? Let's forget about all this brochuremanship from the contractors who have a vested interest in selling the airplane. And it's always talked about, but it's never really put into practice. And the specs never are fulfilled. Even the C-17, which is a very popular transport airplane, never lived up to its original specs.
Towards the end, when it was clear that the A-12 was not going to stay, the Navy tried to show that it was still a valid concept. And so if you were to sit in those meetings, they were meeting all the goals that the Navy had set up for, not necessarily the first goals that they set in the contract, but the ones the Navy sort of caved in on over time. The Navy wanted this airplane desperately. It was a love-hate relationship. The A-12 program was so secret that When I showed a document to former Vice Admiral Robert Dunn, who was in charge of the aviation operational side in the Navy, I put the document down. He picked the document up, he looked at it, he looked at me, and he looked at it and he looked at me, he looked at it again and he looked at me, and he said, you know, when I signed this, I never thought it would see the light of day. He said, I should have listened to my good friend, and he named his friend. He said, never sign anything unless you expect to see it on the front page of the Washington Post. And that document that he signed was basically telling someone he wanted to work back channel, that he didn't want to have to divulge this information to the Congress for fear that Congress would shut down the program when it started running into problems in the very beginning. It was in the mind of Herb Fenster, the attorney that represented the A-12 team, or at least the GD component of it. Admiral Dunn's failure to notify the Congress was the single most duplicitous act in the entire A-12 program. At the first trial, the contractors won. And they won because they were suing the Navy, saying that you failed to terminate the contract properly. You failed to follow the 7 steps. The judge agreed, awarded the contractors by changing it from termination for default to a termination for convenience. The Navy said, or should I say, the Justice Department lawyers representing the Navy, they said, well, wait a minute, Judge, we can show egregious default. In other words, they first said, well, there was criminal activity, and the judge says, well, show me the criminal activity. And they said, well, we can't find that, but we can show you egregious behavior, which they call the egregious default trial. So for about a year, that went on. And the only thing that the Navy could show was that the contractors were overweight by 704 pounds. And of course, that was ludicrous because there have been many other programs that have been overweight far more than that are still flying today. The A-12 began life with unappropriated money. What that means is that the prohibition in the Constitution, which says the executive branch cannot spend money unless Congress has approved it, spend it anyway. And the way the Navy got around it was it has a lot of black programs, and it would take these black programs and put it into a big pool, kind of like a winemaker. Instead of going to the Naval Air Systems Command, where the money should have gone, where it was appropriated to, it went to the Naval Supply Systems Command, into a fund. And in that fund, they mixed the money together like they're blending wine, like the French do. And then they would ladle out the money wherever it was needed. And this was found out because there was a label left on some of that money that said it was for another purpose. So that was one of the counts in the ultimate lawsuit. So the unappropriated money doesn't really slow down the military services if they want to violate the law. And it is a felony to violate the law, because Congress in the early 1800s was getting all these bills for things that never approved. So Congress got tired of that and decided to make it a felony. And have you ever heard of anyone being prosecuted for that? I have. Some people ask me, who is the villain in this case? What they don't understand is the way decisions are made in the Department of Defense. Most of these decisions are group decisions. That way, everybody shares the blame, and there's nobody that they can point their finger at. It's this fungibility of responsibility. Nobody's responsible.
There was a decision made, which again, each of you have used the word we. Was it put in writing, Admiral Morris? Yes or no? Somewhere you all have used the we, and we're going to find out who we is.
And her staff.
Whose decision was it to make? Was it your decision? Whose decision was it?
Now, in the case of Cheney, he is responsible for canceling the contract just a few months after he said it was well handled, and he asked for more money for it. So the reason he canceled it is obviously not because it wasn't well handled. He'd said it was, unless he was lying. It's not because he didn't because he had the money. He didn't have the money, so he had to make a decision. What am I going to do? So he canceled the program so he could get them out of the picture, get them terminated for default, free up the money for the war. And by the way, right after that, he allowed the contractors to not pay up. They had an agreement in which the contractors could defer paying the $1 billion that they owed, or whatever the amount was, which is unheard of. It's no precedent for it. They still haven't paid any money. They're supposed to pay when you get terminated for default and then come back and collect it. There are the question is, what did the contractors actually deliver? Well, in their contract, there's a whole bunch of line items, and they delivered most all of that. After the contract was terminated, there was a video taken that I saw that showed all the parts that have been made, and you can basically see all the parts for an airplane. You could have put an airplane together with, I would say, almost a complete airplane with all those parts that were there. So it isn't as though they didn't do anything. Well, one of the big problems they ran into was curing the laminates that they were using with the special approach to building airplanes, which wasn't out of metal, it was out of composites. Well, who knew about that technology? Northrop knew about it. Lockheed knew about it. Navy didn't know about it. They could have told them in a heartbeat how to do it, but it was too late. The Navy is invoking the State Secrets Act, which I find somewhat ironic, because when Undersecretary of Defense Kaminsky was asked in his deposition, is there any technology from the A-12 program that is viable, that you can use, it's something that the government or the people can use? He said, no, not really. So here they're arguing about state secrets over an airplane where the Undersecretary of Defense, who is a specialist in stealth, says there's nothing in the A-12 program we need. The A-12 case, after 20 years, is now in the Supreme Court. They had oral argument in January of 2011. And one of the ironies is that when the A-12 contractors were ready to file their lawsuit, they talked to the government and said, tell you what, we won't sue you if you don't sue us. We'll just walk away. So here we are 20 years later. We're in the Supreme Court, and the argument is based on the State Secrets Act, which legally means the following. It means that the government, if it wants to invoke the State Secrets Act, is supposed to pay the contractors because it's for the privilege of taking the State Secrets Act. One lawyer I talked to, Herb Finster, who was the first attorney for the Mac Air GD team, said that a case called Windstar requires that they pay the contractors if they're going to invoke the State Secrets Act. What I found ironic was Justice Scalia argued, gee, that doesn't seem fair. Why don't you guys just walk away with what you've got now? So the whole thing has come around after 20 years to that being one of the arguments. And I don't know what's going to happen, but whatever happens, the taxpayer lost in the end. For years, the McDonnell Douglas company had been trying to sell the Navy an airplane they called the Hornet 2000, which was an airplane that was bigger than the F-18C and D, but it was going nowhere. Towards the end of the A-12 program, there was an argument being made that we should probably just stop the A-12 and put the money into the F-18 Hornet 2000, which was then being called the F-18E. There was a big meeting, study was done, and the study concluded that there's no way that the F-18E could do the job of the A-12 because you'd have to put RAM, this radar-absorbing material, over all of its weapons which hang externally, and that it was absolutely inadequate for the job. The second that the A-12 program was canceled, they dusted off that Hornet 2000/F-18E and said, oh, this is the answer, because the Navy is paranoid about not having its aircraft carriers. And if they don't have an airplane, they don't have a justification for deep strike, which they call it, bombing the enemy way internally, then they have no justification for the carrier, and then basically the Navy has no justification for an air wing. So that was their very sensitive spot. So the airplane that they were bad-mouthing a month previously. A month later, they were saying, this is the answer, we can do this. And by the way, they violated all kinds of internal rules, getting that appropriated by just bypassing the rules that were required to justify the airplane in the first place.
They say the F-18 is just a remake of the old F-18. It's frankly 80% all new. The F-18 E and F, as one admiral put it to me, is good enough. And there is, as I say, a point where if you have an airplane too expensive, you can't buy enough of them to justify the carriers. Well, the F-18 E and F is plenty good enough for the threat out there. And it's easier to maintain than would have been the A-12. And yes, all pilots like to go fast and have fancy gadgetry in their airplane. But when you look at who's got any sophisticated airplanes out there, where is the threat? I mean, they talk about China, but China has only got a minuscule Air Force. They talk about Russia. Russia's more bankrupt than we are. So, in my view, what fails to be done is to justify a new product on the basis of a potential enemy threat. That was never done, and it's never done. It's become a kind of a gee whiz game to how can I make it more sophisticated, more complicated. But I think it's time to call time out and say, hey, look, we're putting airplanes out of carrier. There's all kinds of corrosion problems. There's all kinds of training problems. You got to land at night. You got to land in rough seas. What are we doing here with all this fancy stuff that is marginally important? So, you know, they keep talking about automating carriers, and then they say, well, how do you fight a fire, which is the biggest single threat on an aircraft carrier? You get 5,000 kids on an aircraft carrier, and if something catches fire, it could be very explosive. And so every time they talk automation of a carrier to save money, they always end up saying, well, you need the firefighting capability, so we still got 5,000 people on a carrier. And it's very manpower intensive. It's a human wave attack to run a carrier. And the same way with the planes. You've got amateurs out there on the flight deck who are doing very dangerous work, working their tails off 18 hours a day. Let's give these kids a break by making things less complicated. The aircraft carrier is the heart of the naval fleet. And you have to ask yourself the question, though, if you can't afford enough airplanes to justify 11 aircraft carriers, what are you going to put out there? So you're shooting yourself in the foot, in a sense, by having an airplane so expensive you can't afford to buy enough of them to fill up the decks of the carrier. And the present Secretary of Defense in our country, Bob Gates, has said, we've got 11 aircraft carriers and nobody else has more than one. And he made the point that that's a ridiculous ratio, but he said, quote, I'm not crazy. In other words, Congress loves the aircraft carriers too, because the Navy's been lobbying for them forever. And so it's reaching a point of diminishing returns when you have an aircraft carrier which costs $30 to $40 billion. When I first started covering defense, it was $3 billion. And you got a cruise missile which can disable the flight deck, which is all you have to do. You don't have to sink the carrier to put it out of service. I mean, what good is a carrier if it can't deliver ordnance on the target? What good is a carrier if it doesn't have airplanes it can take off? And so all you have to do is use $1 million cruise missile, surface-to-surface cruise missile, to disable the flight deck of a carrier for weeks. So you put it out of action, and what good is it going to do you off Libya, for instance, if they hit it with a surface-to-surface missile? So the whole mix is, to my mind, in need of a strategic review as opposed to this rubber stamping of what we're already doing, which is the quadrennial defense review, which Congress has mandated they do every 4 years. But it's a piece of boilerplate. It just justifies what we're doing. We really need a rigorous review of where we're going on defense. And to save money, I think Obama made a terrible mistake by giving defense a free pass and saying, we're going to cut everything but defense. And then he backed off and said, well, defense is on the table too. But Congress is not going to cut defense budget because A, they don't want to look weak on defense. B, they don't care whether a weapon works right or not, as long as it provides jobs in their home area. So we're in a military-industrial complex that doesn't make sense, in my view. Well, you know, one of the good things that Defense Secretary Robert McNamara did, he proved before Vietnam drowned him and Lyndon Johnson as well, that a dollar put in the civilian economy provides more jobs than a dollar put in a weapon. And that's the way he closed surplus bases. And I think we need to go back to sobering up and stop being on this high-tech binge we're on, A, to save money, and B, to get over the idea that any dollar spent in my home area as a politician is good for me because it promotes jobs. That same dollar put into highways or education would have more of a return. And he sold that concept early on in the 60s, but we've lost sight of it. And the fact that we're spending $1 trillion a year on national defense makes no sense at all to me.
There's something about this shape that still feels futuristic. No fuselage, no tail, just wing. But what you're looking at isn't new. It's a design that's been trying to prove itself for nearly a century. This is the Northrop N9M, a small experimental aircraft built to answer a very big question. What if the most efficient airplane was nothing more than a wing? That question didn't stay small for long. By the end of World War II, it had grown into something massive. The YB-35, a bomber unlike anything the world had ever seen. No tail, no compromises, just pure flying wing. And decades later, the idea would finally come of age. The B-2 Spirit, a design once considered radical, now defined the future of air power. Long before stealth bombers were even a dream, a podiatrist named Dr. Cloyd Snyder was chasing an unusual idea, inspired not by bird, but by the shape of a shoe insert. In 1932, launched by car and guided more by curiosity than certainty, it was one of the earliest attempts to answer a question engineers were just beginning to ask. Could an airplane be nothing more than a wing?
Here's the airplane of the future, according to its inventor, Dr. Snyder. He calls it the flying wing, and experts think it's going to revolutionize aviation. It's supposed to be foolproof and has lots of speed and pep, as the doc's going to show you right now. Here she goes. Looks as if the inventor copied his idea from a butterfly.
Not a butterfly, but a powered evolution of Snyder's glider, the S2. Just as the first flying wings were taking to the sky, a young aircraft designer named Jack Northrop was taking off on his own, forming a new company, the Northrop Corporation, in El Segundo, California. Born in Newark, New Jersey, and raised in Santa Barbara, California, Northrop came of age just as aviation itself was being born. He was drafted into the Army during the First World War, and like many in his generation, left it with his eyes on the sky. By 1923, he joined the Douglas Aircraft Company, entering an industry that was still wide open and full of possibility. From the very beginning, he showed a natural instinct for design, combining practical experience with a growing